Langchain experimental rlchain base event summary. This YAML document provides a summary of the langchain experimental reinforcement learning rlchain. It outlines its purpose, inputs, outputs, steps, prerequisites, fine-tuning parameters, and challenges along with potential fixes. The rlchain is designed for building conversational AI systems by leveraging reinforcement learning techniques. Inputs: the user's input, representing the text or query provided by the user. For instance, a user might ask what is the capital of France? The prior conversation history, comprising a record of previous user inputs and the AI responses generated in the conversation. This historical data allows the rlchain to maintain context and consistency throughout the conversation. For example, if a user asks what is the capital of France, and then follows up with and what is its population, the rlchain can use the previous response to understand the context and provide the relevant information. Outputs: the is response, which is the generated output provided by the rlchain based on the user input and the conversation history. This output aims to be informative, relevant, and coherent within the context of the ongoing conversation. For example, in response to the user's query, "What is the capital of France?" the AI response could be, "The capital of France is Paris." Steps: receive user input. This step involves capturing the user's text or query. Process input with language model. This involves feeding the user's input and the conversation history into a language model such as GPT 3.5 or GPT-4. The language model then analyzes the input and generates a representation that can be used to formulate a response. Generate response based on model output. Based on the language model's output, the rlchain generates a response. This response is then presented to the user as the is response to their input. Prerequisites: language model. A language model is a fundamental component of the rlchain. It is responsible for understanding the user input, processing it, and generating a response. Examples of commonly used language models include GPT 3.5 and GPT-4. Developed by OpenAI. Reward function. A reward function defines the criteria used to evaluate the quality of the is responses. It helps the rlchain learn which responses are considered good or bad based on specific criteria. This could involve human feedback, where humans evaluate the responses and provide ratings. Or it could be based on task completion, such as providing correct answers to factual questions. Fine-tune parameters. Reward function weights. These weights determine the relative importance of different criteria used in the reward function. For instance, if the rlchain is designed to generate engaging responses, the weight associated with user engagement might be higher than the weight associated with factual accuracy. Model parameters. These are the internal parameters of the language model that are adjusted during the fine-tuning process. Adjusting these parameters can improve the model's ability to generate responses that are more relevant, informative, and engaging. Challenges and fixes. Reward function bias. The reward function might inadvertently favor certain types of responses, leading to biased or limited AI outputs. For example, if the reward function primarily focuses on factual accuracy, the AI might prioritize providing correct answers even if they are not engaging or relevant to the conversation. To address this challenge, using diverse human feedback is crucial. This involves obtaining feedback from a variety of users with different perspectives and backgrounds, ensuring that the AI learns from a broader range of viewpoints. Model hallucination. This refers to the tendency of language models to generate incorrect or fabricated information. This can occur due to the limitations of the training data or the model's inherent tendency to extrapolate beyond its knowledge base. A common fix for model hallucination involves fine-tuning the model with factual data. This involves providing the model with a large dataset of accurate and reliable information, which helps the model to improve its understanding of factual concepts and reduce the likelihood of hallucinations. Langchain experimental rlchain base event. A reinforcement learning chain that enhances the performance of language models by incorporating user feedback into the training process. Inputs. The user's text input, which is the initial prompt or query given to the language model. For example, write a poem about a sunset. The text output generated by the language model in response to the user input. For example, a poem about a sunset, which could be evaluated by the user. Outputs. The updated weights of the language model, which are adjusted based on the user feedback to improve its performance. This involves fine-tuning the model parameters to generate outputs that align better with user preferences. Metrics such as accuracy, fluency, and relevance that measure the performance of the language model after training with user feedback. For example, the model could be evaluated on its ability to generate accurate and relevant poems that meet user expectations. Steps. This involves setting up the necessary components for the reinforcement learning process, including defining the environment, reward function, and model architecture. This step lays the foundation for training the model on user feedback. Collecting user feedback, such as ratings, rankings, or feedback on the quality of the model's output, is crucial for guiding the training process. This feedback acts as a reward signal that reinforces desired model behaviors. This step involves updating the language model's weights based on the collected user feedback, aiming to improve its ability to generate outputs that meet user expectations. This step leverages the principles of reinforcement learning to optimize the model's performance based on user feedback. Prerequisites. A pre-trained language model is required, which provides the initial foundation for the reinforcement learning process. The model needs to have some basic understanding of language and be able to generate text before it can be fine-tuned with user feedback. A user feedback mechanism is essential for collecting and incorporating user preferences into the training process. This mechanism could be a simple interface for users to rate or provide feedback on the model's outputs, or a more sophisticated system that allows for nuanced feedback. Fine-tune parameters. The learning rate determines the step size for updating the model's weights based on user feedback. A higher learning rate means the model adjusts its weights more aggressively based on feedback, while a lower learning rate leads to more gradual adjustments. The reward function defines how user feedback is translated into a numerical reward for the language model. A well-designed reward function encourages the model to generate outputs that align with user preferences and goals. For example, a reward function could assign higher rewards to outputs that are accurate, fluent, and relevant to the user's request. Challenges and fixes. Data sparsity refers to the limited availability of user feedback, which can hinder the training process. This issue arises because obtaining feedback from users can be time-consuming and expensive. To address this challenge, synthetic data can be generated to augment the real user feedback, providing more training data for the model. Designing an effective reward function that accurately reflects user preferences and goals is crucial for successful training. The reward function should be aligned with human-aligned metrics, such as accuracy, fluency, and relevance, to ensure that the model learns to produce outputs that are valued by users. Overfitting to user feedback occurs when the model learns to generate outputs that are highly tailored to the specific feedback it has received, but may not generalize well to new users or different types of input. Regularization techniques, such as adding penalties to the model's complexity, can be employed to mitigate overfitting and improve the model's ability to generalize to unseen data. Langchain experimental rlchain base event summary. This embedder leverages the OpenAI application programming interface API to convert text into numerical representations called embeddings. Inputs. Text. This embedder accepts text as input. Outputs. Embedding. The output of this embedder is a numerical representation of the input text, known as an embedding. Steps. Convert text to tokens. The text input is first broken down into smaller units called tokens. Encode tokens to embedding. The tokens are then encoded into a numerical vector representing the meaning of the text. Prerequisites. OpenAI API key. To utilize the OpenAI API, a valid API key is required. This key grants access to the API and manages usage limits. Obtaining an API key typically involves signing up for an OpenAI account and accessing the API key. Settings. Key. The API key is a unique identifier used to authenticate requests to the OpenAI API. OpenAI model. This embedder requires an OpenAI model to perform the embedding process. Various models are available with different capabilities and costs. Model. OpenAI offers a range of models, such as text embedding ADA 002, each designed for specific tasks and offering varying performance and pricing. Fine-tune parameters. Model. The specific OpenAI model used for embedding can be fine-tuned to optimize the embedding process. Different models may provide better performance for specific types of text or tasks. Temperature. The temperature parameter influences the creativity of the embedding process. A higher temperature introduces more randomness, while a lower temperature produces more predictable results. Challenges and fixes. No internet connection. If the code running the embedder lacks internet connectivity, it cannot access the OpenAI API. Run code in environment with internet access. Ensure the code is executed in an environment with a stable internet connection to enable communication with the OpenAI API. API key limit exceeded. The OpenAI API has usage limits based on the chosen plan. Exceeding these limits can lead to errors. Use API with sufficient limit. Select an OpenAI API plan that aligns with the expected usage volume. Invalid API key. An incorrect or expired API key will prevent access to the API. Check API key and ensure valid. Verify the API key entered and ensure it is valid and has not expired. Model not available. The specified OpenAI model might be unavailable due to maintenance or other reasons. Specify valid OpenAI model. Ensure the model name is accurate and currently available. Consult OpenAI documentation for the latest model names and availability. Model configuration issue. Incorrect configuration parameters for the chosen OpenAI model can lead to errors. Use valid configuration parameters. Reference OpenAI documentation for the correct configuration parameters required for the selected model. API request error. Network issues or server-side errors can lead to API request failures. Check network connection and retry. Verify the network connectivity and retry the request if the issue persists. Consider contacting OpenAI support for assistance. Embedding output format mismatch. The format of the embedding output might be incompatible with downstream applications. Validate output format and convert if needed. Ensure the output format matches the expected format for downstream applications. If necessary, Convert the output format using appropriate tools or libraries. Embedding dimensionality issue. The embedding dimensionality might not be suitable for the intended use case. Use compatible embedding size for downstream tasks. Choose an embedding model that produces an embedding size compatible with the downstream task. Performance issues. Embedding process performance can be impacted by factors such as input text length and model parameters. Optimize input text length and model parameters. Consider optimizing the input text length by using summarization techniques or exploring different OpenAI models known for their performance efficiency. Cost considerations. Using the OpenAI API for embedding can incur costs based on the selected model and usage volume. Use API with optimal pricing plan. Choose an OpenAI API plan that best balances cost and performance for the project's needs. Langchain experimental, rlchain, base, selected summary. None. An rlchain is a type of chain that uses reinforcement learning to learn how to perform a task. It takes in an input, uses a language model to generate a response, and then gets feedback on the quality of that response. It uses this feedback to update its internal model, improving its performance over time. Inputs. The input to the rlchain is the task to be performed. This could be a prompt, a question, or a set of instructions. For instance, it could be a prompt like write a poem about a cat, a question like what is the capital of France, or a set of instructions like summarize this article. The rlchain also takes in a reward function. The reward function is used to evaluate the quality of the response generated by the language model. This reward function could be a simple rule-based system, like a predefined set of rules, or it could be more complex, like human feedback or a more sophisticated algorithm. Outputs. The output of the rlchain is the response generated by the language model. The response is based on the input task and the rlchain's learned model, which is updated based on feedback from the reward function. Steps. The rlchain takes in an input and uses the language model to generate a response. The input is the task to be performed, and the language model is used to generate a response that attempts to fulfill the task. The rlchain then uses the reward function to evaluate the quality of the response. The reward function is used to assess how well the response meets the task's requirements. The rlchain uses this feedback to update its internal model, improving its performance over time. The feedback from the reward function is used to improve the rlchain's internal model, allowing it to generate better responses to similar tasks in the future. Prerequisites. The rlchain requires a language model to generate responses. Language models are large neural networks trained on massive datasets of text. They can understand and generate human-like text. Popular examples include GPT-3, GPT-4 and Lambda. The rlchain also requires a reward function to evaluate the quality of the responses. A reward function is a way to assess the quality of the response generated by the language model. It can be based on predefined rules or human feedback. Fine-tune parameters. The learning rate determines how much the rlchain adjusts its internal model based on each piece of feedback. The learning rate is a parameter that controls how much the rlchain changes its internal model in response to each piece of feedback. The discount factor determines how much the rlchain values future rewards compared to immediate rewards. The discount factor is a parameter that controls how much the rlchain values future rewards compared to immediate rewards. Challenges and fixes. The rlchain can be slow to learn, especially if the reward function is complex or the task is difficult. if the reward function is complex or the task is difficult. The RL chain may require a lot of data and time to learn effectively. Possible solutions include using a more efficient learning algorithm or simplifying the reward function. The RL chain can get stuck in local optima, meaning it may not find the best possible solution to the task. Sometimes, the RL chain may get stuck in a local optimum, a situation where it has found a good but not necessarily the best solution. Possible solutions include using a more sophisticated exploration strategy or using a larger dataset of examples. Langchain experimental RL chain base selection scorer summary. A base class for selection scorers, responsible for scoring a set of candidate outputs based on a set of criteria. This class is crucial for reinforcement learning agents that need to make decisions based on a set of potential outputs. It provides the framework for evaluating these outputs and determining which one is most likely to lead to a desired outcome. Inputs. A list of candidate outputs, which represents the different options available to the agent at a given point in time. These could be potential responses to a user query, actions in a game, or any other type of decision. The current state of the agent, which captures the agent's current knowledge and context. This could include the history of previous interactions, the current goal of the agent, or any other relevant information. Outputs. A dictionary that maps each candidate output to a score. This score reflects the likelihood of that output leading to a desired outcome based on the current state of the agent. Steps. The selection scorer first initializes a set of candidate outputs. This could involve generating multiple potential responses, actions, or decisions based on the current state of the agent. Next, the selection scorer scores each candidate output based on the current state. This involves evaluating each candidate output against a set of criteria, such as its relevance to the current task, its likelihood of achieving a desired outcome, or its potential impact on the agent's overall performance. Prerequisites. A model that can evaluate the quality of candidate outputs. This model could be a language model, a machine learning algorithm, or any other type of model that can assess the quality of outputs based on a set of criteria. Fine-tune parameters. The weight of each evaluation metric. Different evaluation metrics may have varying importance depending on the specific task. Fine-tuning the weight of each metric allows the selection scorer to prioritize certain criteria over others, ensuring that the most relevant factors are taken into account when scoring candidate outputs. Challenges and fixes. Scoring complex outputs can be challenging as it requires a model that can effectively understand and evaluate the output. To address this challenge, it is essential to utilize a model that is capable of evaluating complex outputs. This could involve using a more sophisticated model, training the model specifically on complex outputs, or incorporating domain-specific knowledge into the evaluation process. Handling outputs with varying lengths can be another challenge, as shorter outputs may be unfairly penalized compared to longer outputs. One common approach to address this challenge is to normalize scores by output length. This ensures that outputs of different lengths are evaluated on a fair basis. For example, a shorter output that is highly relevant to the current state could be given a higher score than a longer output that is less relevant. This normalization process helps to ensure that the selection scorer is able to effectively compare and rank outputs of varying lengths. Langchain experimental RL chain-based selection scorer summary. A core component within the reinforcement learning chain RL chain framework. The selection scorer is responsible for assessing the quality of various potential actions that an agent could take, ultimately guiding the agent's decision-making process. Inputs: a collection of potential actions that the agent could execute in a given state. These actions represent a set of choices available to the agent, each potentially leading to different outcomes. Outputs: a numerical score assigned to each action in the input list. The score quantifies the predicted value or desirability of each action, providing a basis for the agent to choose the most promising action. Higher scores correspond to actions that are likely to be more beneficial or productive in achieving the overall goal. Steps: evaluating each action's potential contribution to achieving the defined goal. This involves applying a scoring function or algorithm that considers factors such as the action's expected reward, its impact on the current state, and its potential to progress towards the desired end state, returning the calculated scores for each action. These scores are then utilized by the rlchain to guide the agent's selection of the next action to execute. Prerequisites: a clearly defined goal that the agent is striving to achieve. This goal provides a target or objective that guides the agent's actions and serves as the basis for evaluating the quality of different actions. A method or metric to measure the agent's progress towards the defined goal. This allows for quantifying the effectiveness of different actions and provides feedback to the agent about its performance. Fine-tune parameters. Parameters that control the reward function, which determines the value assigned to different outcomes or actions. These parameters can influence the agent's preferences and its tendency to pursue certain actions over others. A parameter that determines the relative importance of future rewards compared to immediate rewards. A higher discount factor gives greater weight to rewards that are further in the future, while a lower factor emphasizes immediate rewards. This parameter can influence the agent's long-term planning and its willingness to defer immediate gratification for potential future benefits. Challenges and fixes. Challenge 1: biased scores. Fixes to challenge 1. Carefully designing the reward function to avoid inherent biases that could unfairly favor certain actions over others. This involves considering all relevant factors and ensuring that the reward function accurately reflects the desired goal without introducing unintended preferences. Challenge 2: unstable training. Fixes to challenge 2. Utilizing techniques such as regularization or normalization to stabilize the training process. These techniques help to prevent the model from overfitting to the training data and improve its ability to generalize to unseen situations. Regularization adds constraints to the model's parameters, preventing them from becoming too large or too complex, while normalization helps to scale the data and prevent large values from dominating the training process. Integration challenges arise when integrating Amazon Personalize with existing systems, such as websites, mobile applications, or data pipelines. These challenges might include compatibility issues, API integration complexities, and customizing API responses. Potential solutions involve choosing appropriate integration methods, using APIs provided by Amazon Personalize, and potentially developing custom integration components. Monitoring and evaluation is essential for assessing the performance of the recommendation system and identifying areas for improvement. This involves tracking key metrics such as click-through rates, conversion rates, and user satisfaction, evaluating the quality of recommendations, and potentially retraining the model based on the insights gained. Langchain experimental rlchain. Reinforcement learning chain for langchain is a framework that enables the use of reinforcement learning techniques to train language models for complex tasks. This approach utilizes a trial and error learning paradigm, where the model interacts with an environment, receives feedback in the form of rewards, and adjusts its actions based on those rewards. Inputs. Prompt is the input to the reinforcement learning chain, which serves as the context for the task and influences the actions taken by the model. For example, a prompt might be write a short story about a cat who goes to space. Reward function defines the criteria for evaluating the actions taken by the model. It quantifies the desirability of each action in the context of the task. A well-defined reward function is crucial for guiding the model towards successful outcomes. For instance, in a chatbot, the reward function might be based on user satisfaction, measured by metrics such as response time, clarity, and relevance. Outputs. Action represents the output of the reinforcement learning chain, which is the specific action taken by the model in response to the prompt. This action could be a generated text, a decision, or any other action relevant to the task. For instance, in a task involving text generation, the action would be the generated text itself. Steps. Generate action based on prompt refers to the process of utilizing the prompt to produce an action. This step often involves employing a language model to generate a response based on the prompt and the current state of the environment. For example, given the prompt write a short story about a cat who goes to space, the model might generate a sentence like the cat, named Mittens, was a curious creature with a thirst for adventure. Execute action refers to the actual execution of the action generated by the model in the environment. This involves interacting with the environment and receiving feedback on the action's consequences. For example, in a chatbot, this step involves sending the generated response to the user and observing their reaction. Calculate reward based on result involves evaluating the consequences of the executed action and assigning a reward based on the defined reward function. For example, in a chatbot, the reward might be based on the user's response, such as "that's interesting" or "I understand." Update model based on reward involves adjusting the model's parameters based on the received reward, effectively learning from its experiences. The goal is to improve the model's ability to take actions that maximize rewards in the future. This step uses techniques from reinforcement learning, such as gradient descent, to update the model's internal representations. Prerequisites. RL environment is a simulated or real-world environment in which the model learns to perform the task. It defines the rules, constraints, and potential outcomes of the interaction between the model and the world. Popular libraries for creating RL environments include GIM, Stable Baselines 3, and Ray. For example, in a game like chess, the environment would be the chessboard, the pieces, and the rules of the game. GIM, Stable Baselines 3, Ray are popular libraries that provide tools and frameworks for creating and working with reinforcement learning environments. GIM is a toolkit for developing and comparing reinforcement learning algorithms, while Stable Baselines 3 is a library offering a collection of state-of-the-art reinforcement learning algorithms. Ray is a distributed framework for running large-scale reinforcement learning experiments. Reward function is a crucial component of the reinforcement learning process, defining the criteria for evaluating the actions taken by the model. It quantifies the desirability of each action in the context of the task. A well-defined reward function is crucial for guiding the model towards successful outcomes. For instance, in a chatbot, the reward function might be based on user satisfaction, measured by metrics such as response time, clarity, and relevance. Reward for each action is a specific numerical value assigned to each action taken by the model, based on its impact on the task and the defined reward function. For instance, in a game, the reward could be positive for winning a level and negative for losing. Fine-tune parameters. Learning rate determines the step size taken during model updates. It controls how much the model adjusts its parameters based on the received reward. A higher learning rate leads to faster learning but can also lead to instability, while a lower learning rate ensures stability but may result in slower learning. Discount factor controls the importance of future rewards compared to immediate rewards. It discounts future rewards by a factor of gamma, where gamma is a value between 0 and 1. A higher discount factor emphasizes future rewards, while a lower discount factor prioritizes immediate rewards. For example, in a game, a higher discount factor would prioritize actions that lead to long-term wins, even if they don't immediately result in points. Challenges and fixes. Reward function is not well defined is a common challenge in reinforcement learning. If the reward function is not carefully designed, it can lead to unintended consequences, such as the model learning to exploit loopholes or shortcuts instead of achieving the desired outcome. For instance, if the reward function in a chatbot only considers the length of the response, the model might learn to generate very long and irrelevant responses simply to maximize the reward. Define a clear reward function for the task is crucial to ensure that the model learns to perform the desired task effectively. The reward function should be aligned with the task's objectives and incentivize the model to take actions that lead to successful outcomes. In the chatbot example, a better reward function might consider factors such as user engagement, information accuracy, and overall helpfulness. Model struggles to learn is another common challenge in reinforcement learning. This could be due to various factors, including a poorly defined reward function, insufficient data, or inappropriate model parameters. Adjust learning rate and discount factor are common strategies for addressing model learning challenges. Tuning these parameters can help the model converge faster and avoid getting stuck in local optima. Experimenting with different learning rates and discount factors can help find the optimal values for the specific task and environment. Model is biased towards certain actions is a potential issue that can arise if the model learns to exploit biases in the reward function or the training data. For example, if the model is trained on a dataset where certain actions are consistently rewarded, it might become biased towards those actions even if they are not the optimal choice in all situations. Explore different reward functions and model architectures is a common approach for addressing model biases. Using multiple reward functions can help diversify the model's learning and prevent it from becoming overly reliant on a single reward signal. Similarly, experimenting with different model architectures can introduce new biases and encourage the model to explore a broader range of actions. Langchain experimental rlchain base policy summary. A chain that leverages reinforcement learning techniques to generate policies, which are sets of rules or strategies that guide an agent's behavior in a given environment. This chain is designed to learn optimal policies by interacting with the environment and receiving feedback in the form of rewards. Inputs. Prompt. This is a textual input that provides context and instructions to the chain. For example, the prompt might describe the desired goal or behavior of the agent. Environment. This represents the simulated or real-world setting in which the agent operates. It defines the rules, states, actions, and rewards of the system. Examples of environments include game environments, e.g., Atari games, board games, robot simulators, or real-world robotic systems. Outputs. Action. The chain outputs an action based on the current state and the learned policy. The action represents a decision made by the agent in the environment. This could be moving in a game, controlling a robot arm, or taking other actions based on the specific environment. Steps. Initialize environment. This step sets up the environment, including defining the initial state, rules, and reward function. Generate initial state. This step determines the starting state of the environment. This might involve randomly assigning a starting position or configuration to the agent. Get initial action based on the initial state and the current policy. The agent chooses an initial action. Loop until completion. This loop iteratively executes the following steps until a termination. Condition is met, e.g., reaching a goal state, exceeding a time limit, or completing a specific number of steps. Take action. The agent performs the selected action in the environment. Update environment. The environment changes in response to the agent's action. This could involve transitioning to a new state, receiving a reward, or updating the environment based on specific rules. Get next state. After taking an action, the environment transitions to a new state. Get reward based on the current state and the taken action. The agent receives a reward. This reward signal provides feedback to the agent about the quality of its action. Update agent. The agent uses the received reward to update its policy. This involves adjusting the parameters of the learning algorithm based on the rewards and actions taken. This step is central to the learning process as it allows the agent to improve its policy over time. Get next action based on the new state and the updated policy. The agent chooses its next action. Prerequisites. Agent. This refers to the learning algorithm used by the chain to generate policies. It is typically a machine learning model that can learn from experience and improve its performance over time. Examples of agents include deep neural networks, reinforcement learning algorithms e.g., Q-learning, DQN, A3C, and other machine learning models that are suitable for decision-making tasks. Stable baselines. 3. A popular and well-maintained open-source library providing a collection of state-of-the-art reinforcement learning algorithms in Python. It offers a wide range of algorithms, such as DQN, A2C, PPO, and SAC, and supports various environments, including GIM. It simplifies the implementation and experimentation with reinforcement learning methods. Environment. This represents the simulated or real-world setting in which the agent operates. It defines the rules, states, actions, and rewards of the system. Examples of environments include game environments e.g., Atari games, board games, robot simulators, or real-world robotic systems. GIM, an open-source toolkit for developing and testing reinforcement learning algorithms. It provides a wide range of standardized environments, making it easier to implement and compare different algorithms. Reward function. This function defines how the agent is rewarded for its actions. It determines the value of each state and action in the environment. A well-designed reward function is crucial for guiding the agent towards the desired behavior. It can be as simple as awarding a reward for reaching a goal state or as complex as providing rewards based on multiple factors, such as efficiency, speed, and safety. Fine-tune parameters. Learning rate. This parameter controls the step size taken during the policy update. A higher learning rate allows for faster learning but can lead to instability. A lower learning rate provides more stable learning but can be slower. Discount factor. This parameter determines the importance of future rewards relative to immediate Rewards. A high discount factor emphasizes long-term rewards, while a low discount factor focuses on immediate rewards. Exploration rate. This parameter controls the balance between exploring new actions and exploiting known actions. During training, the agent needs to explore different actions to discover new and potentially better strategies. However, once the agent has some experience, it should exploit the actions that have been shown to be successful in the past. Challenges and fixes. Sparse reward. In some environments, the agent only receives rewards for specific actions or reaching certain states. This can make it challenging for the agent to learn, as it may not receive enough feedback to improve its policy. Reward shaping. This involves modifying the reward function to provide more frequent and informative rewards. For example, the agent could be rewarded for making progress towards the goal state, even if it hasn't reached it yet. Reward shaping can help the agent learn more quickly and efficiently. High dimensionality. When the environment has a large number of states and actions, it can be difficult for the agent to learn an effective policy. Dimensionality reduction. Techniques like feature extraction or state aggregation can be used to reduce the dimensionality of the environment, making it easier for the agent to learn. Long-term dependencies. Some environments have actions that have long-term consequences, making it challenging for the agent to predict the future and make optimal decisions. Recurrent neural networks. These types of neural networks can learn temporal dependencies in the data. They are particularly well suited for handling environments where the agent's actions have long-term consequences. Data scarcity. In some cases, it may be challenging to collect enough training data for the agent to learn an effective policy. Transfer learning. This involves using knowledge from a related task to speed up the learning process for a new task. For example, an agent that has learned to play one Atari game might be able to transfer some of its knowledge to a different Atari game. Overfitting. The agent may overfit to the training data, meaning that it learns to perform well on the training data but performs poorly on unseen data. Regularization. This involves adding constraints to the learning process to prevent overfitting. Regularization techniques include L1 and L2 regularization, dropout, and early stopping. Slow convergence. It may take a long time for the agent to learn an effective policy. Optimization algorithms. Advanced optimization algorithms can be used to speed up the learning process. Examples include ADAM, RMS prop, and SGD with momentum. Evaluation. Once the agent has learned a policy, it is important to evaluate its performance. Monte Carlo evaluation. This involves running the agent on the environment multiple times and averaging the results to get a measure of its performance. Hyperparameter tuning. The performance of the agent can be sensitive to the choice of hyperparameters, such as the learning rate, discount factor, and exploration rate. Grid search. This involves trying different combinations of hyperparameters and evaluating the performance of the agent for each combination. Bayesian optimization. This is a more efficient method for hyperparameter tuning that uses a probabilistic model to guide the search for optimal hyperparameters. Langchainexperimental, rlchain, pick best chain, pick best summary. A chain that selects the most suitable result from a collection of outcomes produced by various chains. This process involves evaluating and ranking the results based on a defined scoring mechanism. Inputs. A compilation of chains used for generating outcomes. Each chain represents a distinct approach or method for processing the input data. A collection of input data points to be provided to each of the chains. This input could include text, code, or any other type of data that the chains are designed to handle. Outputs. The outcome deemed the most optimal from the set of results generated by the chains. This selection is guided by the scoring function, which assigns a numerical value to each result based on its quality, relevance, or other criteria. Steps. Execute each chain within the list using the provided input data. Each chain processes the input independently, resulting in a distinct output. Employ a scoring function to evaluate and rank the outcomes generated by the chains. The scoring function determines the relative quality or suitability of each result based on specific metrics or criteria. Return the result that receives the highest score from the scoring function. This signifies the outcome deemed the most favorable or relevant based on the defined criteria. Prerequisites. A collection of chains intended for generating results. The choice of chains should align with the nature of the input data and the desired outcome. A scoring function designed to evaluate and rank the results generated by the chains. This function serves as the basis for selecting the optimal result. Fine-tune parameters. The specific scoring function utilized for ranking the results. The selection of the scoring function should be guided by the desired criteria for evaluating the outcomes. The number of results to be generated from each chain. This parameter controls the amount of data processed by each chain and can influence the diversity of the results. Challenges and fixes. The scoring function might not be capable of accurately assessing and ranking the results. This could be due to the function's design, limitations, or the complexity of the data. Employ a different scoring function or refine the current scoring function to enhance its accuracy and effectiveness. For instance, adjust the weights assigned to different criteria in the scoring function or introduce new metrics that better reflect the desired outcome. The chains might not be able to generate a diverse set of results. This could be due to the chain's limitations, biases, or the homogeneity of the input data. Utilize a different collection of chains or refine the existing chains to promote diversity in their outputs. This could involve including chains with different functionalities, perspectives, or training data. Alternatively, explore methods for augmenting the input data to introduce greater variability. Langchain-experimental rlchain pick best event. A mechanism to select the most suitable chain from a collection of potential chains. This selection is based on the chain's performance when applied to a particular task. Inputs. A collection of candidate chains to be assessed. Each chain represents a distinct sequence of steps or operations designed to address a specific task. A task or a set of tasks to use for evaluating the candidate chains. This serves as a benchmark to assess how well each chain performs. Outputs. The chain that excels in performance during the evaluation task. This is determined based on the established criteria for evaluating chain performance. Steps. 1. Train a reinforcement learning RL agent to evaluate the performance of chains on the given task. This involves providing the RL agent with a set of chains and their corresponding performance scores for the task. The agent then learns to predict the performance of unseen chains. 2. Employ the trained RL agent to evaluate the candidate chains. The agent assesses each candidate chain and provides a prediction of its performance based on its learned model. 3. Identify the chain that receives the highest reward from the RL agent. The reward function, defined during the training phase, reflects the desired outcome for the task. The chain with the highest reward is considered the best performing chain. Prerequisites. A collection of candidate chains to evaluate. Real-world example: consider a set of candidate chains designed to generate summaries for news articles. These chains could include different techniques for text summarization, such as using keyword extraction, sentence extraction, or abstractive summarization. A task or a set of tasks to use for evaluation. Real-world example: the evaluation task could be to generate summaries for a set of news articles, and then compare the generated summaries to human-written summaries. Fine-tune parameters. The reward function used to train the RL agent. This function defines the criteria for evaluating chain performance and assigns a numerical reward based on how well each chain meets these criteria. The hyperparameters of the RL agent. These parameters control the learning process of the RL agent. Examples include the learning rate, the discount factor, and the exploration rate. Challenges and fixes. The RL agent may not effectively learn to evaluate the performance of chains. This can occur when the training data is insufficient or when the reward function does not accurately reflect the desired performance. Solutions. Implement a more sophisticated RL agent that is better suited for the task. Adjust the reward function to more accurately reflect the desired performance of the chains. The evaluation task may not be representative of the real-world task. This can lead to the selection of a chain that performs well on the evaluation task but poorly on the real-world task. Solutions. Use a more realistic evaluation task that better mirrors the real-world scenario. Incorporate a diverse set of evaluation tasks to ensure that the selected chain is robust and generalizable. Langchainexperimental, rlchain, model repository summary. A class for storing and retrieving models used by rlchain, which is an extension of the LangChain framework, and is designed for building reinforcement learning-based applications. Inputs. Name of the model to be stored. This represents the unique identifier for a model within a repository. For instance, you might have a model named BERT for sentiment analysis, which could be referenced by its name in the model repository. File path where the model is saved. This is the location on your system where the model files are stored. For example, it could be a directory path like modelsbit for sentiment analysis containing the model weights and configuration. Additional arguments for model instantiation. This input allows you to specify extra parameters needed when loading and creating an instance of the model. These might include hyperparameters, learning rates, or other configuration settings. Type of the model. This specifies the kind of machine learning model you are using. For instance, it could be BERT for a bidirectional encoder representations from transformers model, or LSTM for a long short-term memory network. Configuration file for the model. This input allows you to provide a configuration file that defines the model architecture and other settings. Such a file might be in JSON or YAML format. The model itself. This is the actual model object, which might be pre-trained or trained from scratch. It contains the model's architecture, weights, and potentially other information necessary for its operation. Outputs. The retrieved model. This output represents the model object that has been successfully loaded from the model repository. Steps. Initial setup of the model repository. This step involves creating a new model repository instance and setting up its initial state. It could involve initializing internal data structures or connecting to a database where models are stored. Adding a new model to the repository. This step takes the provided model inputs and stores them within the model repository. It likely involves creating entries in a database, writing model files to disk, or both. Retrieving an existing model from the repository. This step uses the provided model name or identifier to fetch the corresponding model from the model repository. The process might involve retrieving data from a database or reading model files from disk. Obtaining the list of models currently available. This step provides a comprehensive inventory of all the models currently stored in the model repository. This could be useful for discovering what models are available or for auditing the contents of a repository. Removing a model from the repository. This step allows you to delete a model from the model repository. It might involve removing entries from a database, deleting model files from disk, or both. Prerequisites. Minimum version of Python required. This requirement ensures that your Python environment meets the minimum version for using the model repository class. Version of langchain library required. This requirement makes sure that your installation of the langchain library is compatible with the model repository class. Fine-tune parameters. Name of the model to be stored. This parameter allows you to customize the name of the model within the repository file path where the model is saved. This parameter lets you specify the location where the model files are stored on your system. Additional arguments for model instantiation. This parameter enables you to fine-tune the model's creation by providing specific parameters or configurations. Type of the model. This parameter defines the kind of machine learning model you are using, allowing for flexibility in the type of models you can work with. Configuration file for the model. This parameter allows you to specify a configuration file that defines the model's architecture and other settings, enabling more fine-grained control. The model itself. This parameter represents the actual model object, allowing you to use different models or versions of the same model with the model repository. Challenges and fixes. Challenge 1. The model repository might be filled with models that are not needed. This challenge occurs when the repository contains models that are no longer used or are outdated. Fixes to challenge 1. Delete the models that are not needed. This fix involves removing the unused models from the repository to keep it organized and efficient. Challenge 2. The model repository might be empty. This challenge occurs when the repository lacks any models, making it impossible to retrieve them for use. Fixes to challenge 2. Add models to the repository. This fix involves adding models to the repository, either by training new models or importing pre-trained models. Challenge 3. The model repository might be corrupted. This challenge occurs when the data within the repository is damaged or inconsistent, potentially leading to errors during model retrieval. Fixes to challenge 3. Recreate the model repository. This fix involves rebuilding the repository from scratch, either by manually re-adding models or by using a backup. Challenge 4. The model repository might not be accessible. This challenge occurs when the repository cannot be accessed due to permissions issues, network connectivity problems, or other factors. Fixes to challenge 4. Check the permissions and access to the repository. This fix involves verifying that the user has the necessary permissions to access the repository and that any network issues are resolved. Challenge 5. The model repository might be too slow. This challenge occurs when retrieving models from the repository takes a significant amount of time, potentially impacting performance. Fixes to challenge 5. Optimize the storage and retrieval methods. This fix involves optimizing the methods used to store and retrieve models, such as using faster databases or efficient file storage techniques. Challenge 6. The model repository might not be compatible with the current version of langchain. This challenge occurs when the repository is not designed to work with the latest version of the langchain library, leading to compatibility issues. Fixes to challenge 6. Update the model repository to the latest version. This fix involves upgrading the repository to ensure compatibility with the current LangChain version. LangChain experimental rlchain pick best chain pick best. A chain that utilizes a reinforcement learning agent to select the most suitable chain from a collection of potential chains. Inputs: a collection of candidate chains. Each chain within this collection should be a LangChain chain. For example, consider a scenario where you have multiple chains designed for different tasks, such as summarizing text, translating languages, or generating creative content. The pick best chain would receive this list of chains as input. A dictionary of arguments that will be passed to each of the candidate chains. This dictionary would contain the necessary parameters for each chain to operate correctly. For instance, if you have a chain for translation, the dictionary might include the source language and the target language as key-value pairs. Outputs: the output produced by the most effective chain. This output will be presented as a dictionary. The dictionary will contain two key-value pairs, the output generated by the chosen chain, the name of the chain that was used to generate the output. Steps: the reinforcement learning RL agent is initialized with the provided list of candidate chains. This step involves setting up the RL agent and providing it with the available options for performing tasks. The RL agent engages with the environment by executing each of the candidate chains and observing the outcomes of their execution. This step involves running each chain with the provided arguments and recording the results. The RL agent learns from the outcomes of these interactions and updates its policy. This step involves the RL agent analyzing the results of the chain executions and adjusting its internal strategy to make better decisions in the future. The RL agent selects the best chain based on its current policy. The RL agent uses its learned policy to choose the chain that is most likely to produce the desired output for the given task and inputs. Prerequisites: a collection of candidate chains. Each chain should be a LangChain chain. For instance, you might have chains for summarizing text, translating languages, generating creative text formats, and so on. A dictionary of arguments to pass to the candidate chains. This dictionary would contain the necessary parameters for each chain to operate correctly. For example, if you have a chain for translation, the dictionary might include the source language and the target language as key-value pairs. A reinforcement learning agent. An RL agent is a type of artificial intelligence that learns to make decisions by interacting with an environment. For example, you might use an RL agent trained on a dataset of text summaries to help your chain select the best summarization chain for a given input text. Fine-tune parameters. The learning rate of the RL agent. The learning rate controls how quickly the RL agent adjusts its policy based on new information. A higher learning rate results in faster learning but can also lead to instability. A lower learning rate results in slower learning but can lead to more stable results. The number of episodes to train the RL agent for. An episode is a sequence of interactions between the RL agent and the environment. The more episodes the RL agent is trained on, the better its policy will become. However, training for too many episodes can lead to overfitting, where the RL agent learns the training data too well and performs poorly on new data. Challenges and fixes. The RL agent may not converge to a good policy if the training data is not sufficiently diverse. In other words, if the agent is only exposed to a limited range of inputs and outputs, it might not learn to make good decisions for all possible scenarios. Increase the number of training episodes. Increasing The number of training episodes can help the RL agent see a wider range of data, leading to a more robust policy. The RL agent may overfit to the training data. Overfitting occurs when the RL agent learns the training data too well and performs poorly on new data. This is analogous to a student memorizing the answers to a specific set of exam questions but failing to understand the underlying concepts and struggling when presented with new questions. Use a regularization technique, such as dropout. Regularization techniques are methods that are used to prevent overfitting. Dropout is a technique that involves randomly dropping out units neurons in the RL agent's network during training. This forces the agent to learn more robust representations that are not overly reliant on any single unit. Summary of langchain experimental RL chain pick best random policy. A chain that randomly selects the best chain from a set of candidate chains based on their performance on a set of training examples. Inputs: a list of candidate chains, which are different ways of performing a task, like summarizing a document or answering a question. A list of training examples, which are examples of the task being performed, including the input and the desired output. Outputs: the best chain, which is the chain that performed the best on the training examples. Steps: train a set of candidate chains on a set of training examples. This involves running each chain on the training examples and evaluating its performance. Randomly select the best chain from the set of candidate chains. This is done by randomly choosing a chain from the set of chains that performed the best on pay training examples. Prerequisites: a set of candidate chains, such as a chain that uses a large language model to summarize a document. A chain that uses a question answering model to answer a question. Or a chain that uses a knowledge graph to answer a question. Chain 1, Chain 2, Chain 3. A set of training examples, such as a set of documents and their summaries. A set of questions and their answers. Or a set of questions and their corresponding knowledge graph entities. Example 1, Example 2, Example 3. Fine-tune parameters. The number of candidate chains to train, which is the number of different ways of performing the task that are considered. The number of training examples to use, which is the number of examples of the task being performed that are used to train the chains. Challenges and fixes. The chain may not always select the best chain, which is because the chain is randomly selecting a chain from the set of chains that performed best on the training examples. Increase the number of candidate chains and training examples, which can help to improve the accuracy of the chain. The chain may be biased towards certain types of chains, which is because the chain is trained on a set of training examples that may not be representative of all types of tasks. Use a more diverse set of candidate chains, which can help to reduce the bias of the chain. Langchain experimental, rlchain, VW logger, VW logger. This is a logger for rlchain, the reinforcement learning framework, using the Paul-Wabbert library. This logger tracks and records all the events and data associated with your rlchain pipeline, allowing you to analyze and optimize your reinforcement learning model. Inputs. The input to this logger is the RL chain itself, which encompasses the entire pipeline of reinforcement learning, including the environment, agent, and learning algorithm. Outputs. The Paul-Wabbert logger produces logs in the Paul-Wabbert format. These logs contain information about the events that happened during the RL chain execution, such as the state of the environment, the actions taken by the agent, the rewards received, and the policy updates. Steps. First, The Vaupol-Wabbert logger initializes itself by configuring the logging parameters and establishing a connection to the Vaupol-Wabbert server, if one is being used. Once initialized, the logger continuously logs events from the rlchain. This includes logging the initial state of the environment, the actions taken by the agent, the rewards received for each action, and any policy updates made by the learning algorithm. Prerequisites: the Vaupol-Wabbert library needs to be installed and available on the system where the rlchain is running. This can be done through a package manager or by compiling from source. Fine-tune parameters. The VW-args parameter allows you to fine-tune the behavior of the Vaupol-Wabbert logger. This parameter takes a string of Vaupol-Wabbert arguments, which control various aspects of the logger, such as the format of the logs, the level of logging detail, and the logging frequency. Challenges and fixes. If Vaupol-Wabbert is not installed on your system, the logger will not be able to function. The solution is to install Vaupol-Wabbert. This can be done through a package manager, such as apt or yum, or by compiling from source. The installation instructions can be found on the Vaupol-Wabbert website. If the VW-args parameter is incorrect, the logger may produce unexpected or incorrect logs. The solution is to consult the Vaupol-Wabbert documentation to understand the available arguments and their meanings. You can then modify the VW-args parameter to ensure that the logger functions as intended. Langchainexperimental, rlchain, base, based on. This is a base class for reinforcement learning chains that depend on a specific language model. Inputs: a text prompt that the language model will process to generate a response. A memory structure that holds the history of interactions and can be used to inform the response. Generation. Outputs: the response generated by the language model based on the prompt and potentially the memory. The reward value calculated by the reward function, assessing the quality of the generated response. Steps: 1. Initialize the chain by providing the desired language model and the reward function to evaluate the responses. 2. Input the prompt and memory to the chain. 3. The chain utilizes the language model to generate a response based on the prompt and memory. 4. The reward function is used to assess the quality of the generated response, and a reward value is calculated based on predefined criteria. 5. The generated response and the calculated reward are returned. Prerequisites: a pre-trained language model capable of processing text and generating responses. A reward function that can evaluate the quality of the generated responses based on predefined criteria. Guiding the learning process. Fine-tune parameters. The learning rate determines how much the model adjusts its parameters during training based on pay. Reward signal. A higher learning rate leads to faster adjustments but might result in instability. A lower learning rate ensures stability but may require longer training times. The discount factor defines the importance of future rewards compared to immediate rewards. A higher discount factor prioritizes future rewards, leading to long-term planning, while a lower discount factor prioritizes immediate rewards, resulting in short-term optimization. Batch size refers to the number of training examples used in each update step. Larger batch sizes generally lead to more stable training but require more computational resources. Smaller batch sizes may be faster but can be less stable. Challenges and fixes. Challenge 1: the reward function may not be adequately defined, leading to incorrect feedback and suboptimal learning. Fixes to challenge 1: experiment with different reward functions and carefully analyze their effectiveness based on the desired outcomes. Consider using various reward functions that capture different aspects of the response quality, combining their results to provide a comprehensive evaluation. Challenge 2. The language model may not generate high-quality responses due to limited training data or improper fine-tuning. Fixes to challenge 2. Fine-tune the language model on a data set of relevant prompts and responses that reflect the desired behavior and quality. This can significantly improve the model's ability to generate accurate, relevant, and coherent responses. This process involves adjusting the model's parameters to better fit the specific task and data. Langchain experimental rlchain VW logger summary. The VW logger component logs reward and action data to Warpol Wabbit VW for reinforcement learning. VW is a machine learning library known for its efficiency and effectiveness in handling large-scale data sets. This logger plays a crucial role in enabling the use of VW for training reinforcement learning. Agents. Inputs. Reward represents the numerical value received by the agent based on its actions in the environment. For example, in a game, the reward could be points scored or the level completed. Action represents the specific action chosen by the agent at a particular point in time. This could be a move in a game, a decision in a simulated environment, or an action taken by a robot in the real world. Outputs. VW log data consist of the reward and action data formatted in a way compatible with the Warpol Wabbit library. This data is then used to train the reinforcement learning agent. Steps. Calculate reward. This step involves computing the numerical value of the reward based on the agent's actions and the state of the environment. The reward function defines the specific rules for calculating the reward. Determine action. This step involves the agent choosing an action based on its current state and pay. Available options. This decision can be made using different strategies like random selection, rule-based policies, or learning-based approaches. Log reward and action to VW in this step. The calculated reward and the chosen action are written to the Warpol Wabbit log file. This log file serves as the training data for the reinforcement learning agent. Prerequisites. VW installation requires the Warpol Wabbit library to be installed on the system. This installation can be done using the command VW. VW configuration involves setting up the necessary parameters for VW, including the learning rate, the number of iterations, and the type of model to be trained. The configuration is typically stored in a file named VW config. Fine-tune parameters. VW configuration options. These parameters determine how the VW training process is conducted. Tuning these options can significantly impact the performance of the trained agent. Examples include adjusting the learning rate to control the speed of learning, changing the number of iterations to control the duration of training, and specifying the model type to optimize for different scenarios. Reward function. The reward function defines how the reward is calculated for each action taken by the agent. Designing a suitable reward function is critical for guiding the agent towards desired behavior. For example, a reward function might reward the agent for reaching a specific goal state, penalize it for taking undesirable actions, or provide a combination of both. Challenges and fixes. Incorrect reward calculation. A common issue that arises in reinforcement learning is the incorrect calculation of the reward. This can occur due to errors in the reward function or misinterpreting the state of the environment. Debugging the reward function is crucial to ensure it accurately reflects the desired behavior. Action space mismatch. This issue occurs when the actions available to the agent in the environment do not match the action space defined in the VW configuration. This can lead to errors during training or result in the agent taking actions that are not available in the environment. Adjusting the action space in the VW configuration to match the environment is essential for successful training. VW logging issues. Problems with logging data to VW can occur due to configuration errors, file access issues, or network connectivity problems. It's important to check the VW logs in the configuration to identify and resolve any issues with the logging process. If the log file is not generated or is missing data, it could hinder the training of the agent. Langchainexperimental, rlchain, pick-best chain, pick-best feature embedder. The pick-best feature embedder is a component within the langchain experimental reinforcement learning rlchain library. It leverages embeddings and reward functions to identify the optimal chain for a given task. This selection process is based on the calculated similarity between the input prompt, chain features, and a reward function that quantifies the desirability of different chain outputs. Inputs. The input prompt represents the user's request or query, while chain features are characteristics of different chains that are relevant for the task at hand. These features could include the chain structure, its component modules, or its intended purpose. The reward function is crucial for guiding the selection process. It assesses the quality or relevance of the outputs produced by different chains based on predefined criteria. This function can be based on user feedback, predefined rules, or other metrics that are tailored to the specific task. Outputs. The output of the pick-best feature embedder is the best chain. This chain is chosen based on its similarity to the prompt and its ability to generate desired outputs according to the reward function. Steps. The process begins by embedding the input prompt and the chain features into numerical representations. This embedding step allows for the comparison of different inputs using distance metrics, which measure the similarity between embedded vectors. The next step involves scoring each chain using the reward function and the selected features. This scoring process combines the information from the reward function with the features that are most relevant to the task. The reward function evaluates the chain's output based on user feedback, predefined rules, or other metrics. Finally, the pick-best feature embedder returns the chain with the highest score. This chain is considered the optimal choice for the given task based on the similarity between its features and the input prompt, as well as its ability to produce desired outputs according to the reward function. Prerequisites. A feature embedder is essential for converting textual features of different chains into numerical representations. These numerical representations can be calculated using various embedding methods such as OpenEye embeddings, which leverages pre-trained models from OpenEye, or Hugging Face embeddings, which provides access to a wide range of pre-trained models from the Hugging Face platform. A reward function is crucial for guiding the chain selection process. This function evaluates the quality or relevance of chain outputs based on user feedback, predefined rules, or other metrics. User feedback can be collected through explicit ratings, while predefined rules can be based on domain-specific knowledge or task-specific criteria. Fine-tune parameters. The hyperparameters of the reward function can be tuned to improve the accuracy of chain selection. These hyperparameters determine the weighing of different aspects of the reward function and can be adjusted based on the specific task and the nature of the reward function itself. Challenges and fixes. Feature selection can be a challenging aspect of chain selection. Selecting features that are relevant to the task is crucial for ensuring that they Pick best feature embedder effectively identifies the best chain. Careful consideration should be given to the nature of the task and the types of features that are likely to influence chain performance. Reward function design plays a crucial role in the success of chain selection. It is essential to design a reward function that accurately captures the desired chain behavior and provides a reliable measure of output quality. This design process may involve experimentation and refinement based on feedback from the users or from the task itself. Embedder bias can affect the accuracy of chain selection. Different embedding models may exhibit biases towards specific types of language or concepts, which can lead to inaccurate comparisons between chain features. To mitigate this challenge, it is recommended to use diverse embedders and to explore methods for reducing biases in embedding models. Langchain experimental, rlchain, base, embed and keep summary. A summary of langchain experimental, rlchain, base, embed. This class represents a langchain component that embeds both a query and a document into the same vector space. This allows for comparing the similarity between the query and the document based on their vector representations. Inputs. Query str. This represents the input question or the user query that needs to be analyzed in. Compared to the document, it is a string that contains the user's input. Example: what is the capital of France? Document str. This represents the textual content of the document that will be compared with the user query. This is a string containing the textual content of the document that is being analyzed. Example: Paris is the capital of France. Outputs. Query embedding list. This is a list of numbers representing the vector embedding of the input query. It is obtained by encoding the input query using a pre-trained model like OpenAI. Hugging face or sentence transformers and maps the query to a numerical representation, allowing for similarity comparisons with the document. Example: 0.12345, 0.67890, 0.23456, 0.78901, 0.34567, 0.89012. Document embedding list similar to the query embedding. This represents the vector embedding of the input document. This is a numerical representation of the document obtained by applying a pre-trained model to encode the document's textual content into a vector representation. This allows comparing the similarity between the query and the document based on their vector representations. Example: 0.98765, 0.43210, 0.87654, 0.32109, 0.76543, 0.21098. Steps. 1. Embed the query using the configured embedder. This step involves using a pre-trained embedding model to convert the user query into a numerical vector representation. This model could be from OpenAI, Hugging Face, or sentence transformers, depending on the configuration. Example: Paris would be converted to 0.12345, 0.67890, 0.23456, 0.78901, 0.34567, 0.89012. 2. Embed the document using the configured embedder. Similarly, this step uses the same configured embedding model to convert the input document into a numerical vector representation. This allows for a direct comparison between the query and document embeddings to determine their similarity. Example: France would be converted to 0.98765, 0.43210, 0.87654, 0.32109, 0.76543, 0.21098. Prerequisites. Embedder. This refers to the pre-trained embedding model that is used to convert the query and document into vector representations. These models are trained on massive text datasets and can be accessed through various application programming interface API services or libraries like OpenAI, Hugging Face, or sentence transformers. These models provide the ability to represent the meaning of text in a numerical form. Example: OpenAI offers pre-trained embedding models like Ada, Babbage, Curie, and DaVinci. Document Loader. This component is responsible for loading the textual content of the document into a string format. This is needed to process the document text and embed it into a vector representation. For example, a document loader could be used to load text files, web pages, or PDF documents into a string. Fine-tune parameters. Embedder. This refers to the specific embedding model that will be used to encode the query and document. This allows for choosing the desired model based on factors like accuracy, computational resources, and specific use case requirements. Example: text embedding Ada 002 or OLMPNet base 2. Use cache. This parameter controls whether the embeddings should be cached for future use. This can significantly improve the performance of the embedder by avoiding redundant computations. Enabling caching allows the embedder to store and retrieve previously calculated embeddings, leading to faster retrieval and processing. Challenges and fixes. Challenge 1: memory usage. This refers to the potential issue of large models consuming a significant amount of memory, especially when dealing with large documents or queries. This can lead to performance issues or even system crashes. Example: using a large language model like Text DaVinci 003 might require a significant amount of memory to process long documents. Use smaller models. This is a common solution to address memory usage issues. By selecting a smaller embedding model, the memory footprint is reduced, making it suitable for resource constrained environments. Example: using text embedding Ada 002 instead of Text DaVinci 003 can significantly reduce memory usage. Challenge 2: long documents. This challenge arises when dealing with very long documents that exceed the maximum context length of the embedding model. This can result in incomplete or inaccurate embeddings. Example: a long document containing thousands of words might exceed the maximum context length of a pre-trained model, resulting in partial embedding. Chunk document. Embed chunks and average. This approach involves dividing the long document into smaller chunks, embedding each chunk separately, and then averaging the embeddings of all chunks to get a final representation of the document. This approach allows the embedding of long documents, while minimizing the memory usage and addressing the maximum context length limitations. Example: a document with 10,000 words can be divided into 10 chunks of 1,000 words each. Then each chunk can be embedded and then averaged to get the final embedding of the document. Langchain experimental rlchain base embed summary. A description of the langchain experimental rlchain base embed summary, which combines langchain's reinforcement learning capabilities with embedding based retrieval and its associated components, including inputs, outputs, steps, prerequisites, fine-tune parameters, and challenges and fixes. Inputs. The text input for the RL agent to process and generate responses from which could be a question or a statement, for example, what is the capital of France, or explain the concept of gravity. A list of documents to be used as context for the RL agent, which could be a collection of text Files like Wikipedia articles or news articles or a set of knowledge base entries, for example, a list of countries and their capitals. Outputs: the text generated by the RL agent incorporating relevant information from the provided documents, which could be an answer to a question or an explanation of a concept. For example, Paris is the capital of France, or gravity is a force that attracts objects with mass towards each other. Steps: initialize an RL agent and a document embedding model, which means setting up the reinforcement learning algorithm and the model that converts text into numerical representations, for example, using a pre-trained model like BERT or sentence transformers. Embed the input text and the provided documents, which involves converting the input text and the documents into numerical representations using the embedding model, for example, representing the input text and documents as vectors in a multi-dimensional space. Use the embeddings to retrieve relevant documents, which involves comparing the embedding of the input text with the embeddings of the documents and identifying the most similar documents, for example, finding the documents that are closest to the input text in the embedding space. Use the retrieved documents as context for the RL agent to generate a response, which involves using the retrieved documents as additional information for the RL agent to generate a more informed and accurate response. For example, the RL agent uses the retrieved documents about France to answer the question, what is the capital of France? Prerequisites: install the necessary langchain packages for reinforcement learning and embedding models, which involves installing the required libraries for using reinforcement learning and embedding models in LangChain, for example, installing the LangChain RL and LangChain embeddings packages. Prepare a dataset of text inputs and corresponding responses for training the RL agent, which involves collecting a set of example inputs and their desired outputs to train the RL agent. For example, a dataset of questions and answers or statements and explanations. Fine-tune parameters, learning rate and other hyperparameters for the RL agent, which involves adjusting the parameters that control the learning process of the RL agent. For example, the learning rate determines how much the RL agent updates its parameters based on each training example. Fine-tuning parameters for the embedding model, which involves adjusting the parameters of the embedding model to improve its performance. For example, fine-tuning the embedding model to better represent the specific domain of the input text and documents. Challenges and fixes. Challenges: the RL agent might struggle to effectively utilize the retrieved documents during response generation, which means that the RL agent may not adequately incorporate the information from the retrieved documents into its response. Fixes: experiment with different embedding models and retrieval strategies and fine-tune the RL agent's parameters, which involves trying different embedding models and retrieval methods and adjusting the RL agent's parameters to improve its ability to utilize the retrieved documents. For example, trying different embedding models like sentence transformers or OpenAI's embedding API, or using different retrieval strategies like k-nearest neighbors or semantic search. Challenges: the RL agent might produce responses that are not factually accurate or coherent, which means that the RL agent may generate responses that contain incorrect information or are not logically connected. Fixes: implement mechanisms to ensure that the generated response aligns with the retrieved documents and is factually consistent, which involves developing methods to verify the accuracy and consistency of the generated response, for example, using fact-checking techniques or incorporating mechanisms to ensure that the response is consistent with the retrieved documents. Langchain experimental rlchain base embed summary. Inputs. Text to be embedded. It could be a paragraph, a document, or any other form of textual data. Embedding function, a function that maps text into a numerical vector representation. Capturing semantic meaning. Examples include OpenAI's embedding a P, sentence transformers, and universal sentence encoder. Outputs. Embedded text, the numerical vector representation of the input text, generated by the embedding function. Steps. Embed input text using provided embedding function. This step involves applying the chosen embedding function to the input text to obtain its numerical representation. Prerequisites. Text input, a string representing the text to be embedded. For example, the quick brown fox jumps over the lazy dog. Embedding function, a function that can embed text into a vector representation. For example, the OpenAI embedding a P takes a text input and returns a vector representing its semantic meaning. Fine-tune parameters. Fine-tuning parameters of the embedding function used. These are parameters that can be adjusted to optimize the embedding function for a specific task or dataset. For example, fine-tuning parameters for OpenAI's embedding a P can be used to improve its performance on a specific domain like medical text or legal documents. Challenges and fixes. Handling long text inputs that exceed embedding function limits. Many embedding functions have limits on the length of text they can handle. For example, OpenAI's embedding a P has a maximum length of 4096 tokens. Split the text into smaller chunks and embed each chunk separately to handle long texts. We can split them into smaller chunks that are within the embedding function's limits. Then, we embed each chunk individually and concatenate the resulting vectors to obtain a representation of the entire text. This approach allows us to embed even very long texts. Selecting an appropriate embedding function for the task. The choice of embedding function depends on the specific task and desired semantic representation. For example, if we want to perform text classification, we might choose an embedding function that is specifically designed for this task. Consider the context and desired semantic representation when choosing an embedding function. It is important to consider the context of the task and the desired semantic representation. For example, if we are working with medical texts, we might choose an embedding function that is specifically trained on medical data to ensure that it captures the nuances of medical language. Langchain experimental, rlchain, base, embed list type. A description of the embed list type class defined in the langchain experimental, rlchain, base module, outlining its functionality, inputs, outputs, steps involved, prerequisites, fine-tune parameters, and potential challenges with their respective solutions. Inputs. A list of text inputs to be processed by the embed list type class. These text inputs can be individual sentences, paragraphs, or longer pieces of text. Real-world examples could include customer reviews, product descriptions, news articles, or social media posts. Outputs. A list of embedding vectors, each representing a corresponding text input from the input list. These embedding vectors are numerical representations of the text inputs, capturing their semantic meaning and relationships to other texts. They can be used in various downstream tasks, such as similarity search, clustering, or classification. Steps. Tokenization of the text input. This step involves breaking down the input text into individual words or subword units called tokens. Tokenization is essential for preparing the text for further processing, like embedding. Popular tokenizers include WordPiece, sentence piece, and BPE, each with its strengths and limitations. Embedding the tokens. This step converts each token into a numerical vector representation using an embedding model. This representation captures the semantic meaning of the token in relation to other tokens. Popular embedding models include Word2Vec, Glove, Fast Text, and BERT. These models are trained on massive text datasets and learn to represent words and phrases in a way that captures their meaning and relationships. Prerequisites. An embedding model. This is a crucial prerequisite for the embed list type class. The embedding model is used to convert the tokens into numerical vectors. Choosing the right embedding model depends on the specific task and the available resources. For example, if the task involves understanding natural language, a model like BERT, trained on a large corpus of text, would be a suitable choice. Fine-tune parameters. Embedding model parameters. These are settings that control the behavior of the embedding model. Some common parameters include the size of the embedding vectors, the number of layers in the model, and the learning rate. Tuning these parameters can improve the performance of the embedding model for specific tasks. List of embedding types. This parameter specifies the types of embeddings to be used for representing the text inputs. Different embedding types capture different aspects of the text, such as word meaning, sentence structure, or context. Choosing the appropriate embedding type is crucial for achieving the desired results. Challenges and fixes. Different embedding models. Different embedding models can produce different embedding vectors for the same text input, potentially leading to inconsistencies in downstream tasks. Use an appropriate embedding model based on the task and the data. For example, if the task involves understanding natural language, a model like BERT would be a suitable choice. However, if the task involves classifying documents based on their topics, a model trained specifically for topic modeling might be more appropriate. Different embedding types. Using different embedding types can lead to different representations of the same text input, potentially affecting the results of downstream tasks. Select an appropriate embedding type based on the task and the data. For example, if the task involves understanding the meaning of words, a word embedding model might be sufficient. However, if the task involves understanding the context of sentences, a sentence embedding model might be necessary. Langchain experimental rlchain based get based on and to select from. This describes the fundamental structure of an rlchain class that is designed to pick the best option from a list of choices based on provided input text. This class utilizes reinforcement learning RL principles to learn and adapt its selection process over time. Inputs. This refers to the input text that the RL chain will use to determine the most appropriate choice. This text can be any form of text such as a paragraph, sentence, or even a single word. For example, if the input text is "What is the capital of France?" the RL chain will analyze this text and utilize the list of choices provided to make a selection. This represents a list of choices that the RL chain will analyze and select from. Each choice should be relevant to the provided input text and represent a potential solution or answer. For example, the list of choices could include Paris, Berlin, Madrid, and Rome to correspond to the input text "What is the capital of France?" Outputs. This output represents the choice that the RL chain has selected from the list of choices based on its analysis of the input text. The selected choice should be the most relevant and accurate based on the provided input text. Continuing the example, the expected output for the input text "What is the capital of France?" would be Paris. Steps. This step involves the RL chain generating a list of potential options based on the input text. The generation process can involve various techniques, such as using a language model (LM) or other machine learning methods to analyze the input text and propose potential options. This step involves the RL chain analyzing each of the generated options and evaluating them based on the input text. The evaluation process could utilize various metrics, such as comparing the options with the input text, calculating their similarity, or utilizing a predefined reward function to assess their relevance and quality. This is where the RL aspect of the class comes into play. The RL chain learns from its past experiences and adjusts its evaluation criteria to improve its accuracy over time. In this step, the RL chain selects the best option based on the evaluation performed in the previous step. The selected option is the one that received the highest score or achieved the best result based on the criteria used for evaluation. The RL chain utilizes its learning process to improve its selection accuracy over time by continuously adjusting its evaluation criteria. Prerequisites. This refers to a large language model (LLM) that the RL chain uses to analyze the input text and generate potential options. LLMs are powerful artificial intelligence systems that can understand and process human language. They play a crucial role in the RL chain by providing the foundation for its ability to comprehend and interpret the provided input text. Popular examples of LLMs include GPT-3 and BERT. This refers to an environment that the RL chain operates in. This environment provides the context for the RL chain's learning process and determines the feedback it receives during its training. An environment can be simulated or real-world, and it dictates the conditions under which the RL chain interacts with the world and learns from its experiences. Popular examples of environments include OpenAI gym environments. Fine-tune parameters. This refers to a function that defines the reward or score assigned to the RL chain for each action. It takes a well-designed reward function guides the RL chain towards achieving the desired goal and encourages the selection of options that lead to better outcomes. The reward function is a crucial component of the RL chain's learning process, as it helps the RL chain learn which actions are desirable and which actions are undesirable. This parameter controls how much the RL chain modifies its learning process based on the feedback it receives. A smaller learning rate indicates that the RL chain learns more slowly and makes gradual adjustments to its behavior. Conversely, a larger learning rate implies that the RL chain learns more quickly and adapts its behavior more drastically. The choice of learning rate depends on the specific task and the complexity of the learning environment. Challenges and fixes. Designing an effective reward function is a significant challenge in RL chain development. A poorly designed reward function can mislead the RL chain and prevent it from achieving the desired goal. For instance, if the reward function assigns a high reward for selecting the shortest option, the RL chain might prioritize short options regardless of their accuracy. The solution to this challenge is to carefully design a reward function that accurately reflects the desired goal and rewards the RL chain for making appropriate selections. This refers to the situation where the RL chain's learning process becomes unstable, leading to unpredictable and erratic behavior. Learning instability can occur due to various factors, including a large learning rate, an unsuitable reward function, or a complex learning environment. The solutions to this challenge involve adjusting the learning rate, exploring different reward functions, and implementing early stopping mechanisms to prevent the RL chain from diverging from its optimal behavior. Langchain experimental rlchain.base.is string type instance summary. This component checks whether the input is a string. In essence, it determines if the provided input is a sequence of characters that can be interpreted as text. For instance, hello, world, or 12,345 would be considered strings. However, a numerical value like 12,345 or a Boolean value like true would not be classified as strings. This is important for many programming tasks, as strings are often used for storing and manipulating text data. Inputs. This component accepts an input, which is the data we want to check. The input could be any kind of data, such as a number, a Boolean value, a list, or a dictionary. For example, the input could be hello, world, 1 2 3 4 5, true, or 1, 2, 3. Outputs. The output of this component is a Boolean value, which indicates whether the input is a string or not. If the input is a string, the output will be true. If the input is not a string, the output will be false. For instance, if the input is hello, world, the output will be true. However, if the input is 12,345, the output will be false. Steps. The core functionality of this component is to determine if the input data is a string. This is achieved by checking the type of the input. If the type of the input is a string, the component outputs true. Otherwise, it outputs false. This process involves examining the structure and characteristics of the input to ascertain if it conforms to the definition of a string. Prerequisites. This component does not have any specific prerequisites. It can operate independently without requiring any prior setup or configuration. Fine-tune parameters. This component does not have any fine-tune parameters. The behavior of the component is fixed and cannot be customized through any tunable settings. Challenges and fixes. This component does not have any known challenges or fixes. It is a straightforward component with a well-defined function and does not encounter any known issues. Langchain experimental rlchain.base.is string type instance summary. This function checks whether the input provided is a string type. The input can be of any type. Inputs. The input can be any type of data, such as a number, a string, a list, or a dictionary. For example, the input can be the number 12, the string hello world, the list 1, 2, 3, or the dictionary name John. Age 30. Outputs. Bool. The output of the function is a Boolean value, which is true if the input is a string and false otherwise. For example, if the input is the string hello world, the output will be true. If the input is the number 12, the output will be false. Steps. 1. Check if the input is a string. The function checks if the input is of the string type. This is done by using the built-in Python function as instance. If the input is a string, the function returns true. Otherwise, it returns false. Prerequisites. Python 3.7 or higher. This function requires Python version 3.7 or higher to run. This is because the function uses the isInstance function, which was introduced in Python 3.7. Fine-tune parameters. None. This function does not have any fine-tune parameters. It is a simple function that checks if the input is a string. Challenges and fixes. Challenge 1. If the input is not a string, the function returns false. If the input is not a string, the function will return false. This can be a challenge if the user expects the function to handle non-string inputs. For example, If the user provides a list as input, the function will return false even though the list may contain strings. Fix 1. Ensure that the input is a string before calling the function to avoid this challenge. The user should ensure that the input is a string before calling the function. This can be done by converting the input to a string using the str function. For example, if the input is a list, the user can convert it to a string using the str function and then call the function. This will ensure that the function returns true if the input is a string, regardless of the original data type. Challenge 2. If the input is a string, the function returns true. If the input is a string, the function will return true. This is not a challenge in itself, but it can be important to understand how the function works. Fix 2. Ensure that the input is a string before calling the function to ensure that the function returns true only if the input is a string. The user should ensure that the input is a string before calling the function. This can be done by converting the input to a string using the str function. For example, if the input is a number, the user can convert it to a string using the str function and then call the function. This will ensure that the function returns true only if the input is a string, regardless of the original data type. Elaborated description of the LangChain experimental rlchain basis string type instance function. Method name. The LangChain method prepare inputs for AutoEMD is a core component responsible for preparing data before feeding it into the AutoEMD functionality. AutoEMD is a crucial part of many language processing tasks, as it allows for the representation of textual information in a numerical format suitable for machine learning algorithms. Input details. This method requires two key inputs. 1. Input text, the text that needs to be converted into an embedding, serving as the raw data for the AutoEMD process. 2. Embedding function, a function that takes text as input and outputs an embedding vector. This function determines how the input text is transformed into a numerical representation. Common embedding functions include sentence transformers or OpenAI's embedding API. Output details. The primary output of this method is a list of embeddings. Each element in this list represents the numerical embedding of a corresponding piece of text provided as input. This list of embeddings serves as the structured representation of the original input text, ready for subsequent processing within the AutoEMD functionality. Steps description. This method typically involves two key steps. 1. Extract the input text. The input text is extracted and prepared for processing by the embedding function. This may involve cleaning or pre-processing the text to ensure it is in a suitable format for the embedding function. 2. Use embedding function to convert text to embeddings. The extracted input text is then passed to the embedding function. The function converts the text into a numerical vector representation, known as an embedding. This embedding captures the semantic meaning and relationships of the words within the text. Prerequisites description. The prepare inputs for AutoEMD method relies on the availability of these two prerequisites. 1. Embedding function, a function that takes text as input and outputs an embedding vector. This function is essential for transforming the input text into a numerical representation. 2. Input text that needs to be converted into an embedding. This text forms the basis of the embedding process. A real-world example: suppose you have a customer review, the product is amazing, I love its features. You can use this method to convert this review into a numerical embedding. The embedding function could be sentence transformers or OpenAI's embedding API. Fine-tune parameters description. This method does not have any fine-tune parameters. The process of converting text to embeddings relies primarily on the chosen embedding function and The input text itself. Challenges and fixes description. Challenges and fixes in using this method. 1. Incorrect embedding function. A wrong embedding function can lead to inaccurate and unhelpful embeddings. 2. Input text issues. Issues with the input text, such as invalid characters or incorrect formatting, can hinder the embedding process. Fix for challenge 1. To prevent this challenge, ensure the correct embedding function is selected and that it can properly handle the provided input text. This involves choosing an embedding function compatible with the text format and the desired output, and checking if the function accepts the text as input. For example, if your input text is a single sentence, you might need a sentence embedding model instead of a word embedding model. Fix for challenge 2. To address this challenge, ensure the input text is valid and formatted correctly for the chosen embedding function. This may involve pre-processing the input text by cleaning it of unwanted characters, removing special characters, and converting it to the correct format. For example, if the chosen embedding function requires lowercase text, make sure the input text is converted to lowercase before being passed to the function. Langchain experimental, rlchain, base.get based on and to select from summary. This YAML document describes the langchain experimental, rlchain, base.get based on and to select from function in detail. The function is designed for selecting objects from a list based on certain criteria, and the document provides an overview of its purpose, inputs, outputs, steps, prerequisites, fine-tuning parameters, and potential challenges with solutions. A function that generates a list of objects to select from based on a given set of criteria. For example, imagine a scenario where you have a list of potential candidates for a job and you want to select those who meet certain criteria like having a specific skill set or years of experience. This function can help you filter the candidates based on your requirements. Inputs. A list of objects, each containing a dictionary of key-value pairs representing their attributes. For instance, each object could represent a product with attributes like name, price, and category. A dictionary of key-value pairs representing the criteria to filter the objects by. Using the product example, the criteria dictionary could include key-value pairs like category electronics or price 100. Outputs. A list of objects that match the given criteria. In the product example, this would be the list of products that fall under the specified category and price range. A list of objects that do not match the given criteria. In the product example, this would be the list of products that do not meet the specified category and price range. Steps. Filter the list of objects by the given criteria. This involves comparing the attributes of each object with the criteria dictionary and identifying the objects that meet the specified conditions. Return the filtered objects and the objects that did not meet the criteria. This provides a comprehensive output, allowing the user to analyze both the selected objects and those that were not included. Prerequisites. The list of objects must have a dictionary of attributes for each object. Each object must contain a set of key-value pairs that describe its characteristics. For example, object 1 attribute 1 value 1, attribute 2 value 2. Object 2 attribute 1 value 3. Attribute 2 value 4. The criteria dictionary must contain key-value pairs that match the keys in the object attribute. Dictionaries. The keys in the criteria dictionary should align with the attribute names in the objects. For example, criteria attribute 1 value 5. Attribute 2 value 6. Fine-tune parameters. None. This function does not require any fine-tuning parameters. Challenges and fixes. The criteria dictionary might not contain all the keys in the object attribute dictionaries. In this case, the function can be modified to handle missing keys by returning all objects that have at least one matching key-value pair. For example, if the criteria dictionary only specifies attribute 1, objects with values for attribute 1 and attribute 2 would be considered matching. The criteria dictionary might contain keys that are not in the object attribute dictionaries. To address this, the function can be modified to ignore keys that are not present in the object attribute dictionaries. This ensures that the filtering process is not impacted by extraneous criteria. For example, if the criteria dictionary contains attribute 3 but the object attributes only include attribute 1 and attribute 2, attribute 3 will be ignored. Langchain-experimental, rlchain, base, embed list type determines how a list of documents is embedded. For example, in a search application, a list of documents can be embedded to enable efficient retrieval of relevant documents based on user queries. The embedding process transforms each document into a numerical representation, which captures its semantic meaning. Inputs: a list of documents to be embedded. Each document is typically a text string, but can also include other data types, such as images or audio. For instance, in a knowledge base system, a list of articles can be provided for embedding. Outputs: an embedding for each document in the input list. Each embedding is a vector of numbers, representing the semantic meaning of the corresponding document. For example, the embeddings can be used to perform similarity comparisons between documents, enabling retrieval of relevant documents based on a query. Steps: embeds each document in the list using a specific embedding function. The embedding function maps the text content of each document into a numerical representation, capturing its semantic meaning. This process can be compared to converting words into a numerical code, where similar words have similar codes. Prerequisites: a language model capable of generating embeddings. This is typically a large language model, such as OpenAI's GPT-3, trained on a massive dataset of text and code. It understands the meaning of words and concepts and can translate them into numerical representations, useful for downstream tasks. For example, a language model can be used to embed a document about machine learning into a vector that captures its meaning. A method for embedding documents. This refers to the specific technique used to convert documents into numerical representations. Common methods include transformer-based embedding models, such as sentence transformers, which are trained to generate high-quality document embeddings. An example of a practical application is a news aggregator, which can use these techniques to group similar news articles together. Fine-tune parameters. Embedding function: the specific embedding function used to convert each document into a numerical representation. Popular embedding functions include sentence transformers, OpenAI's Ada embedding API, and Hugging Faces sentence transformers API. These functions are designed to capture the semantic meaning of text and translate it into a vector representation. Embedding: dim the dimensionality of the embedding, which represents the number of features used to represent the semantic meaning of a document. A higher dimensionality allows for capturing more nuances in meaning, but requires more computational resources and storage. A lower dimensionality is computationally efficient but might lose some semantic information. The appropriate embedding Dimension depends on the specific application and the available resources. Challenges and fixes. The language model may not be able to produce embeddings for all documents. This can occur for documents containing unusual language, specialized jargon, or technical terminology. Try using a different language model. Different language models are trained on different datasets and have varying strengths and weaknesses in their ability to understand and represent different types of text. The embedding function may not be able to handle all types of documents. Different embedding functions have varying capabilities in handling different types of documents, such as text, code, or images. Try using a different embedding function. Experiment with different embedding functions that are known to work well with the type of documents in your dataset. The embedding dimension may not be appropriate for the task. The choice of embedding dimension is important and depends on the specific application. Try adjusting the embedding dimension. Experiment with different embedding dimensions to find the optimal balance between capturing semantic meaning and computational efficiency. For example, a higher embedding dimension might be needed for tasks involving fine-grained semantic distinctions, while a lower dimension might suffice for tasks requiring less nuanced understanding. Langchain experimental, Smart LLM, base, Smart LLM chain summary. NaN. A chain that wraps an LLM and provides additional functionality. This means that it takes an LLM as an input and uses it to perform tasks beyond just generating text. It can be used for tasks like question answering, summarization, and translation. For example, a smart LLM chain could be used to take a user's question, send it to an LLM for processing, and then return the answer in a specific format. Inputs. The input to the LLM. This can be any type of text, such as a question, a paragraph, or a list of items. For example, a user might ask the LLM what is the capital of France, and this would be the input. Outputs. The output of the LLM. This is the text that the LLM generates in response to the input. For example, the LLM might respond to the question what is the capital of France with the answer Paris. Steps. 1. Pre-process the input. This step involves cleaning up the input and preparing it for the LLM. For example, this step might involve removing any special characters or punctuation from the input, or converting the input to lowercase. 2. Call the LLM. This step involves sending the input to the LLM and waiting for the LLM to generate an output. 3. Post-process the output. This step involves cleaning up the output and preparing it for the user. For example, this step might involve removing any unwanted text from the output, or converting the output to a specific format. Prerequisites. An LLM. This is a large language model, such as GPT-3 or Llama, which can generate text, translate languages, write different kinds of creative content, and answer your questions in an informative way. LLMs like GPT-3, Llama, etc. These are powerful language models, capable of generating human-like text and performing a wide range of language-related tasks. GPT-3 Generative Pre-trained Transformer 3 is a powerful language model developed by OpenAI. Llama Large Language Model. Meta AI is a large language model developed by Meta AI. A way to pre-process and post-process the input and output. This is necessary to ensure that the input and output are in the correct format for the LLM and the user, respectively. For example, the input might need to be formatted as a list of items, and the output might need to be formatted as a paragraph. Fine-tune parameters. The LLM model to use. This is the specific language model that will be used to process the input and generate the output. For example, you might choose to use GPT-3 or Llama. The temperature of the LLM. This parameter controls the creativity of the LLM's output. A higher temperature will result in more creative output, while a lower temperature will result in more predictable output. For example, a higher temperature might lead to more surprising and unusual answers, while a lower temperature might lead to more consistent and predictable answers. The top K of the LLM. This parameter controls the number of possible outputs that the LLM will consider. A higher top K value will result in the LLM considering more possible outputs, while a lower top K value will result in the LLM considering fewer possible outputs. The top P of the LLM. This parameter controls the probability of the LLM selecting each possible output. A higher top P value will result in the LLM being more likely to select less probable outputs, while a lower top P value will result in the LLM being more likely to select more probable outputs. The max tokens of the LLM. This parameter controls the maximum number of tokens that the LLM will generate in response to the input. A higher max tokens value will result in the LLM generating longer outputs, while a lower max tokens value will result in the LLM generating shorter outputs. Challenges and fixes. Challenge 1: the LLM may not be able to understand the input. For example, the LLM might not be able to understand a question that is phrased in a complex or ambiguous way. Fixes to challenge 1. Use a more powerful LLM. A more powerful LLM will be able to understand a wider range of inputs. For example, a larger LLM with more training data might be better able to understand complex or ambiguous questions. Provide more context to the LLM. By providing more context, you can help the LLM to understand the input better. For example, you might provide the LLM with a background paragraph or a list of related terms. Challenge 2: the LLM may not be able to generate the desired output. For example, the LLM might not be able to generate a response that is relevant to the input, or it might not be able to generate a response that is creative or informative enough. Fixes to challenge 2. Fine-tune the LLM on a dataset that is similar to the desired output. By fine-tuning the LLM on a dataset that is similar to the desired output, you can help the LLM to learn the patterns and relationships that are present in the desired output. For example, if you want the LLM to generate creative stories, you could fine-tune it on a dataset of creative stories. Provide more examples of the desired output. By providing more examples of the desired output, you can help the LLM to learn what kind of output you are looking for. For example, if you want the LLM to generate summaries of news articles, you could provide it with a few examples of news articles and their corresponding summaries. Langchain experimental rlchain base pass lines. A list of inputs expected by the langchain experimental rlchain base pass lines. A list of lines to be parsed. These lines can be of any length and content, such as text from a file or user input. For example, if we are processing a text file that contains multiple lines, each line would be an element in this list. A list of outputs generated by the langchain experimental rlchain base pass lines. The parsed text string containing the lines joined together, removing any new line characters. The output is a single string, which can be used for further processing or display. For instance, The output can be used to generate a summary of the input text or to extract information from it. A list of steps involved in the langchain experimental rlchain base parse lines. Splitting the lines. This step breaks down the list of lines into individual elements, allowing each line to be treated independently. For example, if we are processing a text file, each line in the file will be split into a separate element in the list. Converting the lines to a single string. This step joins the individual lines together into a single string, removing any new line characters between them. For instance, if we have a list of lines representing a paragraph, this step would join all the lines into a single string representing the entire paragraph without any line breaks. A list of packages that need to be installed before using the langchain experimental rlchain base parse lines. The langchain experimental package. This package is a collection of experimental features and tools that extend the functionality of langchain, which is a framework for building applications powered by large language models. The experimental package provides advanced features and functionalities, including reinforcement learning capabilities for improving the performance of language models. A list of challenges faced while building the langchain experimental rlchain base parse lines and their fixes. Handling newline. This challenge arises when processing text that contains newline characters, which are used to indicate the end of a line. These characters can cause problems when converting the text to a single string, as they might be interpreted as part of the text, leading to unexpected results. To address this, we replace newline characters with spaces, ensuring that they are not included in the final string. For example, if the input text contains a newline character between two lines, we would replace it with a space to ensure that the two lines are joined seamlessly. Removing redundant spaces. This challenge is encountered when processing text that might contain multiple consecutive spaces, which can affect the clarity and readability of the output text. This can happen due to inconsistent formatting or the presence of extra spaces in the input text. To eliminate this issue, we use the string strip method, which removes leading and trailing spaces from the string, ensuring that the output text is clean and well formatted. For instance, if the input text contains a sentence with multiple spaces between words, we would use string strip to remove any extra spaces, resulting in a more visually appealing and consistent output. Langchain experimental SQL summary. This Python library empowers users to construct custom SQL queries using natural language prompts, eliminating the need for manual SQL writing. Inputs: a natural language prompt expressing the desired data retrieval request. For example, show me the names of customers who placed orders in the last month. Credentials and information necessary to connect to a specific database. This includes details such as the database type, host address, port number, username, and password. Outputs: the generated SQL query corresponding to the natural language prompt, representing the structured data retrieval command for the database. The results of executing the SQL query on the database, returning the requested data in a format suitable for analysis or presentation. Steps: the natural language prompt is analyzed and interpreted to understand the user's intent and pay desired data retrieval criteria. The parsed prompt is translated into a valid SQL query, ensuring adherence to the syntax and structure of the targeted database system. The generated SQL query is executed against the specified database, retrieving the requested data based on the defined conditions. The retrieved data is formatted and presented in a user-friendly manner, making it easily accessible and understandable. Prerequisites: a database connection library specific to the target database system. Examples include PsychoPG2 for PostgreSQL, MySQL connector for MySQL, and others depending on the database used. The LangChain library, a powerful framework for building and deploying language-based applications. It can be installed using the command pip install langchain. Fine-tune parameters: the specific dialect of SQL supported by the target database. Different databases may have variations in their SQL implementations, requiring specific dialect settings for accurate query generation. The schema of the database, providing information about the tables, columns, data types, and relationships within the database. This allows the library to accurately interpret the natural language prompt and translate it into a valid SQL query. Challenges and fixes: ambiguous prompts when the natural language prompt is unclear or lacks specific details. The library may struggle to understand the user's intent accurately. Addressing this challenge requires crafting prompts that are precise, using clear keywords and constraints to guide the query generation process. Incorrect SQL syntax: due to the complexities of SQL syntax and database-specific variations, the generated query may contain errors. To mitigate this, a SQL parser can be employed to validate the generated query, ensuring its correctness before execution. Missing database information: if the database schema or connection details are not provided, the library cannot effectively generate or execute the query. Providing the necessary database information is crucial for seamless operation. Unsupported database operations: some database systems may have limitations or restrictions on certain SQL operations. It's important to check the supported features of the database and adjust the natural language prompt accordingly. Query performance issues: complex queries or large datasets can lead to performance bottlenecks. To optimize query performance, techniques like indexing, query optimization strategies, and data partitioning can be applied to ensure efficient data retrieval. LangChain experimental rlchain-based stringify embedding summary. Convert text to embedding is the operation performed by this component where text is converted to embedding. For example, when a user types a query like "What is the capital of France?" this component converts the query text to an embedding, which is a mathematical representation of the text in a multidimensional space. This embedding can then be used by other components to find similar texts or to perform other tasks related to natural language processing. Inputs: the input of this component is the text that needs to be converted to an embedding. For example, this could be a user query, a document, or any other text that needs to be represented in a mathematical way. Outputs: the output of this component is the embedding that represents the input text. This embedding is typically a vector of numbers, where each number represents a different dimension of the text's meaning. Steps: the step involved in converting text to embedding is first to get the text as input and then pass it to an embedding model. This embedding model is a machine learning model that has been trained on a large dataset of text and embeddings. The model takes the input text and outputs a vector of numbers that represents the meaning of pay text. Prerequisites: the prerequisites to run this component is that the LangChain library needs to be installed on pay system. LangChain is a framework for building and using language models, and it provides various tools and components for working with text, including embedding models. Fine-tune parameters: the embedding model is the key parameter that can be fine-tuned to achieve better results. Different embedding models have different strengths and weaknesses, and the choice of model can have a significant impact on the quality of the embedding. For example, some models are better at capturing the semantic meaning of text, while others are better at capturing the syntactic structure of text. Challenges and fixes. Challenge 1. The challenge that could be faced is the embedding model might not be available on the system. This could be due to the model not being installed or not being accessible from the current environment. Fixes to challenge 1. The fix for the above challenge is to install the embedding model on the system. This can be done using the appropriate package manager for the system, such as pip for Python. Challenge 2. The challenge that could be faced is the embedding model might not be suitable for the task at hand. For example, if the task is to find similar documents, then a model that is good at capturing the semantic meaning of text would be more appropriate than a model that is good at capturing the syntactic structure of text. Fixes to challenge 2. The fix for the above challenge is to use a different embedding model that is more suitable for the task. There are many different embedding models available, and it is important to choose one that is appropriate for the specific task. Langchain experimental SQL base SQL database sequential chain. Description of langchain experimental SQL base SQL database sequential chain. Inputs. A user-provided structured query language SQL query that specifies the data to be retrieved from the database. A connection string or object that enables the chain to establish a connection with the database. For query execution. Outputs. The results of the executed SQL query returned in a format that is easy for users to understand. Steps. The input SQL query is parsed using a SQL parser to create a structured representation of the query. This structured representation is essential for efficient query execution. The structured representation of the SQL query is used to execute the query against the database. This step involves sending the query to the database engine and retrieving the requested data. The results of the query execution are returned to the user in a user-friendly format. This could involve formatting the data into a table, a list, or any other suitable representation. Prerequisites. Database connection. A valid connection string or object that allows the chain to connect to the database. This connection is essential for executing the SQL query against the database. SQL parser that can process the input SQL query and transform it into a structured representation. This parser is crucial for understanding the query and executing it correctly. Fine-tune parameters. Database connection type. The type of database connection used by the chain examples include MySQL, PostgreSQL and SQLite. The choice of database connection type depends on the specific database being used. SQL dialect. The specific version or dialect of SQL supported by the database. Different database systems may have slightly different SQL syntax. Choosing the correct dialect ensures that the input SQL query is interpreted correctly. Challenges and fixes. Query syntax errors. If the input SQL query contains syntax errors, the chain will not be able to execute the query. This could be due to incorrect keywords, missing parentheses, or other syntax issues. To resolve this, ensure that the input query is valid SQL and compatible with the database dialect. Using appropriate tools or referencing the database documentation. Database connection issues. If the chain cannot connect to the database due to issues like incorrect connection details or database unavailability, the query execution will fail. To fix this, check the connection details including the host name, username, password, and database name. Ensure that the database is accessible and running. Data retrieval errors. Even with a valid connection and a correctly formatted SQL query, errors can occur during data retrieval. This could be due to issues in the query logic such as referencing non-existent columns or tables, or problems with the database schema. To resolve this, check the query logic carefully and ensure that it accurately reflects the database schema referencing the database. Documentation or using database management tools can be helpful in troubleshooting these errors. Langchain experimental SQL base. SQL database sequential chain. A chain that allows to execute structured query language queries and return the results. This chain acts as an intermediary, facilitating the interaction between a user's SQL query and a structured query language database. Inputs. The input to this chain is a structured query language query, a structured way of requesting information from a database. This query can be as simple as retrieving all records from a table or as complex as performing calculations and filtering based on specific conditions. Real-world examples include retrieving the names of all customers who have purchased a specific product or calculating the average price of products in a particular category. Outputs. The output of this chain is the result of the query. This result could be a table of data, a single value, or a message indicating the success or failure of the query execution. For example, a query asking for the average price of products might return a single numerical value, while a query listing all customer names would return a table of names. Steps. First, it creates an SQL database instance. This instance represents the connection to the specific structured query language database. It encapsulates all the necessary information for interacting with the database, including the connection string and the credentials. The database can be any type, including MySQL, PostgreSQL, or SQLite. The next step is to define the query to be executed. This query is the user's input, formatted in the structured query language syntax. It specifies what data to retrieve or manipulate from the database. After defining the query, the chain calls the execute method on the SQL database instance with the query to run the query. This method sends the query to the database for processing, and the database executes the query against its data. Finally, the chain returns the results. The results are the outcome of the executed structured query language query, presented in a format suitable for the user. This format can vary depending on the query and the database. Prerequisites. A SQL database connection is essential for the chain's operation. This connection enables the chain to communicate with the database and execute queries. This connection is established using a database connection string, which contains the necessary information for connecting to the database, and SQL database credentials, which authenticate the user accessing the database. Examples of database connection strings vary based on the database type, but they generally include information about the database server, the database name, and the port number. Fine-tune parameters. Query parameters can be used to further refine the query, allowing for dynamic execution based on specific values. These parameters can be passed to the query at execution time, allowing for more flexible queries. A real-world example could be using a query parameter to filter orders by a specific date range or to specify a product ID for retrieval. Challenges and fixes. An incorrect SQL query is a common challenge. If the syntax or logic of the query is incorrect, the database cannot interpret it and will throw an error. The fix for this is to validate the SQL query before execution. This involves parsing the query for syntax errors and ensuring that the tables and columns referenced exist. Tools like SQL linters can be used for validation. Another common issue is database connection issue. This can arise from incorrect database connection string or credentials, or if the database is not running. The fix for this is to ensure that the database connection string and credentials are correct. Additionally, checking if the database is running is crucial, as a non-functional database will prevent any queries from being executed. Database access permission issue can occur if the user account accessing the database lacks the necessary privileges. This can prevent the execution of certain queries or even accessing specific tables or data. The fix for this is to ensure that the user account has the required privileges to access the database. This might involve granting specific roles or permissions to the user account. Query execution error can happen when the query, although syntactically correct, violates database constraints or accesses data that is not permitted. This can be due to data type mismatches, invalid data, or exceeding database limitations. The fix for this is to check the database error log for more information. Additionally, ensuring that the query is valid and does not violate any database constraints is essential. This involves reviewing the query logic and comparing it with the database schema. Langchain experimental SQL vector SQL retrieve all output parser summary. This parser processes the results of a vector SQL query and returns all the results as a list of dictionaries. It is a key component in the LangChain framework for effectively handling data retrieved from vector SQL, a powerful tool for querying and analyzing data stored in vector databases. Inputs: a list of dictionaries representing the results of the vector SQL query. Each dictionary contains the data from one row in the query results. For example, column 1 value 1, column 2 value 2, column 1 value 3, column 2 value 4. Outputs: a list of dictionaries containing the results of the vector SQL query, where all the values are strings. The output preserves the structure of the input list of dictionaries but ensures that all data values are represented as strings. This makes the output suitable for downstream processing and analysis. Steps: 1. The parser iterates through the list of dictionaries, processing each dictionary individually. 2. For each dictionary, it converts the values to strings. This ensures that all data values are uniform and suitable for various downstream tasks. 3. The parser returns the list of dictionaries with all values converted to strings. This output list is ready for further analysis and use in other parts of the application. Prerequisites: vector SQL query results. This parser requires a list of dictionaries representing the results of a vector SQL query. This list should contain all the data retrieved by the vector SQL query, structured as a list of dictionaries where each dictionary corresponds to a row in the results. For example, column 1 value 1, column 2 value 2, column 1 value 3, column 2 value 4. Fine-tune parameters. None. This parser does not have any fine-tuning parameters. It directly processes the input vector SQL query results and returns a list of dictionaries with string values. Challenges and fixes. Challenge 1. The vector SQL query results may contain values that are not strings. This could be due to the nature of the data or how it is stored in the vector database. Fixes to challenge 1. The parser converts all values to strings. This ensures that all data values are uniformly represented as strings, making the output consistent and suitable for various downstream tasks. This step handles cases where the original values might be numbers, booleans, or other data types. Challenge 2. The vector SQL query results may contain nested dictionaries. This means that some values within the dictionaries might themselves be dictionaries. This can lead to challenges in processing and extracting data from the results. Fixes to challenge 2. The parser flattens the nested dictionaries. This means that all nested dictionaries are converted into a single level of dictionaries, effectively removing nested structures. This simplifies the data structure and makes it easier to work with in downstream tasks and applications. Summary of LangChain experimental SQL vector SQL output parser. This parser is responsible for processing the output generated by vector SQL queries. Vector SQL is a powerful tool that allows you to query data using natural language. The vector SQL output parser helps to bridge the gap between the human-readable vector SQL output and structured data formats, making it easier for applications to utilize the results. Inputs. The input to this parser is the query generated by the user in natural language. For example, a user might ask what is the average price of products sold in the last month. This query would be the input to the vector SQL output parser. A SQL database is required to execute the vector SQL query. This could be any database that supports SQL, such as PostgreSQL, MySQL, or SQLite. The parser needs access to this database to fetch the necessary data. Outputs. The output of the vector SQL output parser is the result of the vector SQL query in JSON format. This JSON format provides a standardized way to represent the data, making it easy for applications to process and utilize the information. Steps. The first step involves parsing the output generated by vector SQL. This step involves extracting relevant information from the vector SQL response, such as the results of the query, any error messages, or warnings. The second step converts the parsed vector SQL output into JSON format. This conversion ensures that the data is structured in a consistent and easily accessible format, suitable for various applications. Prerequisites. Vector SQL needs to be installed on the system to execute the queries and generate the output that the parser needs to process. A SQL database must be set up to provide the data required to answer the user's queries. This setup includes configuring the database, creating tables, and populating them with data. Fine-tune parameters. The vector SQL output parser does not require any specific fine-tuning parameters. It is designed to be a generic parser, capable of handling various vector SQL output formats without requiring adjustments. Challenges and fixes. One challenge is handling errors that might occur during the execution of SQL queries. To mitigate these errors, error handling mechanisms are incorporated into the SQL query. For example, if a table is missing or a column name is incorrect, these errors are caught and handled gracefully, preventing the entire process from crashing. Another challenge is parsing complex vector SQL output. To overcome this, the parser may need to implement custom parsers depending on the specific structure and complexity of the vector SQL output. These custom parsers can be designed to handle complex data structures and ensure accurate data extraction and conversion into JSON format. LangChain experimental SQL vector SQL get result from SQLDB summarization. Retrieves results from a structured query language SQL database using a vector database. This process leverages the power of vector search to find relevant information within a database, enhancing the efficiency and effectiveness of data retrieval. Inputs. A structured query language (SQL) query that specifies the data to be retrieved from the database. A vector database, which is a specialized database designed for storing and searching vectors, representing data points in a multi-dimensional space. Outputs. The results of the SQL query, containing the requested data from the SQL database. A vector embedding, representing the SQL query itself within the vector database. This embedding allows for efficient similarity search within the vector database, finding other similar queries. Steps. Convert the SQL query into a vector representation, encoding the query's semantic meaning into a numerical vector. Search the vector database for vectors similar to the vector representation of the SQL query. This step identifies other queries that are semantically close to the input query. Execute the original SQL query on the SQL database, retrieving the actual data requested by the query. Prerequisites. A connection to the SQL database, including the database name and necessary credentials for authentication and access. A connection to the vector database, including the database name and credentials for accessing and interacting with the vector database. Fine-tune parameters. The index used in the vector database for searching similar vectors. This index defines the structure and organization of the vector data within the database, influencing the search efficiency and accuracy. Parameters that can be included in the SQL query, such as filter conditions, sorting options, or limiting the number of results. These parameters fine-tune the specific data retrieved by the query. Challenges and fixes. Syntax errors within the SQL query. Incorrect syntax can prevent the query from executing correctly. Solutions include carefully reviewing the query syntax for errors and correcting them based on SQL language rules. Connection issues with the vector database, such as incorrect credentials or network connectivity problems. Troubleshooting steps involve verifying connection details, testing network connectivity, and ensuring the vector database is accessible. Slow execution of the SQL query, potentially caused by inefficient query design or lack of appropriate database indexes. Optimizing the SQL query for better performance may involve using indexes, optimizing joins, and limiting the scope of the query. langchainexperimental.sql, Vector SQL, Vector SQL Output Parser. This class parses the structured query language SQL query results obtained from a vector database. It facilitates the extraction of meaningful information from the database by converting raw query outputs into a structured format. Inputs. The results of the SQL query. These results are typically in the form of a list of dictionaries, where each dictionary represents a row in the query output, and the keys of the dictionary correspond to the column names. For example, column 1 value 1, column 2 value 2, column 1 value 3, column 2 value 4 represents the results of an SQL query. Each element in the list is a dictionary, and the keys represent the columns returned by the query. The names of the columns returned by the SQL query. These names are used to map the results of the query to the appropriate column. Outputs. The structured output is a representation of the query results in a user-friendly format. It may be a list, a dictionary, or another data structure that represents the results of the query. The structure of the output depends on the nature of the query and the desired output format. Steps. The process of parsing the SQL query results involves extracting the data from the raw query output. This step involves extracting the data from the SQL query result, which is typically a list of dictionaries, and storing it in a suitable format for further processing. The results are then mapped to the appropriate column names. This step involves matching the data extracted from the SQL query result with the corresponding column names. This mapping helps to organize the data and make it easier to understand. Prerequisites. A vector database is a database that stores data in a vector space. This allows for efficient similarity search, which is important for tasks such as finding similar documents or images. Vector databases such as Pinecone and Chroma are commonly used in various applications. Pinecone and Chroma are popular vector database services. They provide efficient storage and search capabilities for high-dimensional data, enabling applications to retrieve similar items based on their vector representations. For example, they can be used to find similar images based on their visual features or to find similar documents based on their content. SQL query result. The SQL query result is a set of data returned from a database after executing a structured query. Language SQL query. It represents the information retrieved based on the specified conditions and instructions in a query. The result is typically structured in a tabular format, with each row representing a record and each column representing an attribute. For example, a query to retrieve information about customers might return a result with columns such as customer, ID, name, and address. The SQL query result is a list of dictionaries, with each dictionary representing a row in the query output. For example, column 1 value 1, column 2 value 2, column 1 value 3, column 2 value 4 represents the results of an SQL query. Each element in the list is a dictionary, and the keys represent the columns returned by the query. Fine-tune parameters. No fine-tuning parameters are required for this class. It is designed to pass SQL query results without the need for any custom configurations. Challenges and fixes. Different data types may be encountered in the SQL query results, requiring appropriate handling for conversion and processing. Different data types, such as numbers, strings, and dates, might be present in the SQL query results. Conversion and processing of these different data types are essential for ensuring consistent data handling and accurate output. For instance, a numerical value might need to be converted to a string or a date might need to be formatted according to a specific format. These conversions are necessary for correct interpretation and presentation of the data. The SQL query results might contain multiple result rows, which require efficient iteration and processing to extract all the relevant information. When dealing with multiple result rows in SQL query results, it is important to iterate through all rows to ensure that all the data is extracted and processed. This iteration process allows for the handling of each row individually, enabling accurate extraction of information from each row and ensuring that all relevant data is captured. The iteration can involve appending results from each row to a list or another data structure to maintain a consolidated representation of the query results. Langchain-experimental tabular synthetic data OpenEye create OpenEye data generator. This element describes the purpose of the YAML structure. It highlights that this YAML structure outlines a process to create a synthetic data generator that leverages OpenEye capabilities. This generator is specifically designed to produce tabular synthetic data, mimicking real-world datasets with similar characteristics. Inputs. The input to this process is tabular data. This data serves as the training material for the OpenEye data generator. The goal is to learn patterns and structures from this real-world data to generate synthetic data that closely resembles it. For example, if the input tabular data contains information about customer transactions, The generated synthetic data would ideally exhibit similar patterns of purchase behavior, product categories, and spending amounts. Outputs. The output of this process is a data generator that can produce synthetic tabular data. This generator is powered by the OpenAI model and utilizes the learned patterns from the input. Tabular data. The generated synthetic data can be used for various purposes like testing, anonymization, or creating data for research and analysis where real data might be unavailable or sensitive. Steps. The first step involves utilizing the tabular synthetic data module provided by the langchain library. This module facilitates the process of transforming and preparing the input tabular data for use with the OpenAI data generator. The next step is to call the create OpenAI data generator function. This function, likely part of the langchain library or OpenAI API, initializes the OpenAI data generator based on the provided input data. Finally, the input tabular data is passed to the newly initialized OpenAI data generator. This step triggers the training phase where the generator learns from the patterns and relationships present in the real-world tabular data. Prerequisites. This step requires an OpenAI application programming interface API key. This key serves as a credential to access the OpenAI model and its capabilities for generating synthetic data. Your API key is a placeholder for the actual API key, which should be obtained from the OpenAI platform. For security reasons, it is important to treat this key confidentially and not share it publicly. The LangChain library, a Python library for working with language models, is required for this process. It facilitates the interaction with the OpenAI data generator and provides tools for data preparation and management. The command pip install langchain will install the library using the pip package manager. If it is not already installed, fine-tune parameters. The number of synthetic rows represents the quantity of data that the generator should produce. A larger number would result in a more extensive synthetic dataset, while a smaller number would generate a more compact dataset. Column types define the data types of each column in the synthetic data. For example, a column might be defined as a numeric type representing age or a categorical type representing gender. These parameters allow for control over the structure and characteristics of the synthetic data. Challenges and fixes. If the input tabular data does not conform to the format expected by OpenAI, it may need to be converted. This typically involves aligning the data structure and types to match the requirements of the OpenAI model. This might involve data cleansing, transformation, or encoding to ensure compatibility. For example, if the data includes dates, they might need to be formatted in a specific way recognized by the OpenAI model. The OpenAI model may have a limit on the size of data it can process. If the training data exceeds this limit, a smaller subset of the data may need to be selected. This can be done strategically, ensuring that the subset is representative of the overall data while staying within the limitations of the OpenAI model. This could involve sampling data points randomly or selecting specific data ranges that capture the essence of the original dataset. The goal is to retain the key characteristics of the input data while ensuring that the training data size is manageable for the OpenAI model. LangChain experimental tabular synthetic data OpenAI create OpenAI data generator. This YAML file describes the functionality of the LangChain experimental tabular synthetic data OpenAI create OpenAI data generator component. This component uses the OpenAI application programming interface API to generate synthetic tabular data based on a provided data schema. The component is designed to generate synthetic data that mimics the characteristics of real-world data, which can be useful for various purposes such as model training, data augmentation, and privacy-preserving data analysis. Inputs. The provided tabular data is the actual data set that serves as the basis for generating synthetic data. It provides the structure and characteristics that the synthetic data will mimic. The OpenAI API key is a unique identifier that allows the component to authenticate with the OpenAI API and access its data generation capabilities. Outputs. The output of the component is the generated synthetic tabular data. This data mimics the characteristics of the provided real-world data but is synthetically generated. Steps. The first step involves loading the tabular data from the provided source. This step prepares the data for analysis and extraction of schema information. Defining the data schema involves identifying the structure and types of the data columns. This step is essential for generating synthetic data that adheres to the structure of the real-world data. The creation of the OpenAI data generator involves setting up the connection to the OpenAI API and configuring the parameters for data generation. This step utilizes the OpenAI API to create a generator that can produce synthetic data based on the provided schema. Generating synthetic data involves using the created OpenAI data generator to produce a synthetic data set that adheres to the defined schema and characteristics of the real-world data. Prerequisites. The OpenAI API key is essential for authenticating with the OpenAI API and accessing its data generation capabilities. It is a unique identifier provided by OpenAI. Access to the OpenAI API is necessary to utilize its data generation capabilities. This involves having a valid OpenAI account and an active API key. Fine-tune parameters. The number of rows to generate refers to the desired size of the synthetic data set. This parameter allows users to control the quantity of synthetic data generated. The data generation strategy defines the approach used to create the synthetic data. This could involve techniques like Gaussian mixture models, conditional generative adversarial networks (CGANs), or other methods designed to mimic real-world data distributions. Challenges and fixes. Insufficient data for training refers to the scenario where the real-world data set used to train the synthetic data generator is limited in size. This can lead to inaccurate or biased synthetic data. Overfitting to the training data occurs when the synthetic data generator learns the specific patterns and details of the training data too closely, resulting in synthetic data that is highly similar to the real data and may not generalize well to new scenarios. Langchain experimental tabular synthetic data OpenAI create OpenAI data generator. This component creates an OpenAI data generator that can be used to generate synthetic tabular data. This is useful for tasks like data augmentation, privacy protection, and testing machine learning models. Inputs. A pandas data frame that contains the schema of the desired synthetic data. The data frame acts as a template for the synthetic data, specifying the types and relationships between columns. A list of column names that represent categorical features in the data frame. Categorical features are variables that can take on a limited number of distinct values, often represented as strings or labels. Outputs. An OpenAI data generator that can be used to generate synthetic tabular data based on the provided schema and categorical features. Steps. Initialize an OpenAI data generator with the provided data frame and categorical features. This involves providing the generator with the structural information and defining which columns have categorical data. Train the OpenAI data generator on the provided data. This step involves feeding the data to the generator, allowing it to learn patterns and relationships within the data. Prerequisites: OpenAI Application Programming Interface API key. This key is required to authenticate with OpenAI's services and use their API to generate synthetic data. Your unique OpenAI API key, which you can obtain from the OpenAI website after creating an account. OpenAI Python Library. This library provides tools and functions for interacting with OpenAI's API from within your Python code. You can install the OpenAI Python library using the pip package manager by running the command pip install OpenAI in your terminal. Fine-tune parameters. Temperature. This parameter controls the randomness or creativity of the generated data. A higher temperature value leads to more diverse and potentially unexpected data, while a lower temperature value results in data that is closer to the training data. Max tokens. This parameter sets a limit on the number of tokens that can be generated for each row of synthetic data. A token is a basic unit of text, typically a word or punctuation mark. By limiting the number of tokens, you can control the complexity and length of the generated data. Challenges and fixes. The OpenAI data generator may not generate realistic data if the training data is too small or too noisy. Insufficient or poor quality training data can lead to a generator that produces unrealistic or biased data. To address this, consider increasing the size of the training data, ensuring that it is representative of the desired output, and cleaning the data to remove inconsistencies or errors. The OpenAI data generator may generate data that is not representative of the training data. If the generator is not properly trained or tuned, it may produce synthetic data that deviates significantly from the patterns and characteristics of the original data. To overcome this challenge, fine-tune the OpenAI data generator using the temperature and max tokens parameters. Adjust these parameters to control the balance between randomness and faithfulness to the training data. For example, a lower temperature value can help ensure that the generated data closely resembles the original data. Langchain experimental, text splitter, calculate cosine distances. An explanation of the Langchain's text splitter calculate cosine distances method. A list of text chunks, which are smaller units of text extracted from a larger text document. These chunks are used to calculate the pairwise cosine distances. For example, a document could be divided into sentences, paragraphs, or even smaller units. An embedding function, which maps each text chunk to a vector representation in a multidimensional space. The choice of embedding function impacts the quality of the resulting cosine distances. A distance matrix, which represents the pairwise cosine distances between all text chunks. Each element in the matrix corresponds to the cosine distance between two specific text chunks. The resulting matrix allows for insights into the relationships between the text chunks, which can be used in text summarization, information retrieval, and other NLP tasks. A list of text chunks, which is the same list of text chunks that was input to the method. This is useful for keeping track of which text chunk corresponds to each row and column in a distance matrix. Embeds text chunks using the given embedding function. This step transforms each text chunk into a numerical vector representation that captures its semantic meaning. Calculates the cosine distances between the embedded chunks. The cosine distance between two vectors is calculated by taking the dot product of the vectors and dividing by the product of their norms. The resulting value ranges from 0 to 1. Where 0 indicates that the vectors are orthogonal completely dissimilar and 1 indicates that they are parallel completely similar. LangChain installation. A powerful open source library that provides building blocks for creating language AI applications. LangChain is installed using the following command: pip install langchain. Embeddings package, which provides a library for embedding text into numerical vectors. These embeddings allow for representing text as data that can be analyzed and processed by machine learning models. One popular option is sentence transformers, which can be installed using the following command: pip install sentence transformers. Embedding function, which allows you to customize the method by using different embedding models that capture different aspects of the semantic meaning of text chunks. Use batch, a parameter that controls whether the embedding function is applied to the text chunks in batches or all at once. Using batches can help to improve efficiency and reduce memory usage, especially when dealing with large text datasets. Dimension mismatch occurs when the embedding function outputs vectors with inconsistent dimensions. This can happen when using different embedding models or when encountering errors during the embedding process. Ensure that the embedding function outputs vectors with consistent dimensions by carefully selecting and configuring the embedding model, or by debugging the embedding process to identify and correct any issues. Memory issues can arise when processing large text datasets with computationally intensive embedding functions. Use efficient embedding models, such as sentence transformers, which are optimized for performance and memory usage. To further mitigate memory issues, you can process text chunks in batches instead of all at once. LangChain experimental tabular synthetic data. OpenEye create OpenEye data generator. Generates synthetic tabular data based on an OpenEye model that has been trained on similar data. This tool leverages the power of OpenEye models to create new artificial data that resembles the structure and patterns found in the provided real-world data. It is particularly useful when you need to expand your dataset for training machine learning models or for testing purposes. Inputs: a pandas data frame with existing data, used for training the OpenEye model. This is the foundation of the process. The data frame provides the real-world data that the OpenEye model will learn from. It should contain the desired columns and data types that you want to see reflected in the generated synthetic data. For instance, if you need synthetic customer data, you might feed a data frame containing customer names, ages, locations, and purchasing habits. The name of the OpenEye model that will be used to generate synthetic data. This is the key component that powers the synthesis process. You select an OpenEye model that has been trained on data similar to your provided data frame. The choice of model significantly influences the quality and realism of the generated data. Examples of OpenEye models suitable for this task include GPT-3, Codex, and others that excel in text and code generation. Outputs: a pandas data frame containing the synthetic tabular data. The output is the result of the process: a newly generated data frame containing synthetic data that mirrors the structure and patterns of the provided real-world data. This synthetic data can then be used for various purposes like expanding training datasets, testing different scenarios, or performing data analysis tasks without relying on actual user data. Steps: train an OpenEye model on the provided existing data. This step involves providing the real-world data from your data frame to the chosen OpenEye model. The model learns the underlying patterns, relationships, and data types present in the input data. This training process allows the model to understand the structure and characteristics of the data it will later use to generate synthetic data. Use the trained OpenEye model to generate new synthetic data. After the model is trained, You can use it to create new data points that resemble the training data. This generation process involves providing the model with prompts or instructions. And the model then uses its knowledge of the training data to create new rows of synthetic data that adhere to the learned patterns. Prerequisites. An OpenAI application programming interface key is required. This is the key that grants your application access to the OpenAI services. You obtain this key from the OpenAI website, and it is essential for making requests to the OpenAI models. An OpenAI model trained on similar data. This is a pre-trained model that has already been exposed to data similar to your provided data frame. The model's training data influences its ability to generate realistic synthetic data. For instance, if you need synthetic customer data, you would choose a model that has been trained on large datasets of customer information. Fine-tune parameters. The number of rows to be generated in the synthetic data. This parameter controls the size of the synthetic dataset. You can specify how many rows you want the model to generate, which allows you to create datasets of different sizes for your specific needs. The temperature parameter for the OpenAI model. This parameter controls the level of randomness or creativity in the generated data. A lower temperature value produces more predictable and consistent data, while a higher temperature value encourages more varied and potentially surprising outputs. Challenges and fixes. The generated synthetic data might not be realistic. This is a common challenge in data generation, as the model's ability to capture all the nuances and complexities of real-world data is limited. To improve realism, you can adjust model parameters like temperature, increase the amount of training data, or use data augmentation techniques to create more diverse and realistic synthetic data. The model might fail to generate data. This can happen if the provided data is insufficient or the chosen model is not suitable for the task. Ensuring that your training data is diverse and representative of the desired synthetic data. And selecting a model that has been trained on similar data can greatly improve the model's ability to generate data. Langchain experimental text splitter calculate cosine distances summarization. This component calculates the cosine similarity between different text chunks. Cosine similarity is a measure of similarity between two non-zero vectors of an inner product space that measures the cosine of the angle between them. This is commonly used for semantic similarity. For example, if we have two text chunks, the quick brown fox jumps over the lazy dog and a fox jumped over a dog. The cosine similarity between these two text chunks will be high since the two text chunks are semantically similar. Inputs. A list of text chunks. Each text chunk is a piece of text that will be compared to other text chunks. For example, if we have a document, the quick brown fox jumps over the lazy dog. A fox jumped over a dog. The fox is lazy. We can split this document into three text chunks. The quick brown fox jumps over the lazy dog. A fox jumped over a dog. And the fox is lazy. An embedding function. An embedding function takes a text chunk as input and outputs a numerical vector representation of that text chunk. This representation captures the meaning of the text chunk. The embedding function can be a pre-trained model like sentence transformers, OpenAI embeddings, or custom-trained model. Outputs. A matrix of cosine distances between all pairs of text chunks. Each entry in the matrix represents the cosine distance between two text chunks. Steps. 1. Embed each text chunk using the embedding function. This means converting each text chunk into a numerical vector representation. 2. Calculate cosine distances between all pairs of embedded chunks. This is done by calculating the cosine of the angle between each pair of vectors. The cosine distance is a measure of how similar two vectors are. A cosine distance of 1 indicates that the two vectors are identical, while a cosine distance of 0 indicates that the two vectors are orthogonal, completely dissimilar. Prerequisites: text chunks should be preprocessed and cleaned. This involves converting the text to lowercase, removing punctuation, and removing stop words. Stop words are common words like a, and is that do not contribute much meaning to a text. Lowercase conversion converts all the characters in the text chunk to lowercase. For example, converting the quick brown fox jumps over the lazy dog to the quick brown fox jumps over the lazy dog. Removing punctuation removes all punctuation marks from the text chunk. For example, converting the quick brown fox jumps over the lazy dog to the quick brown fox jumps over the lazy dog. Removing stop words removes all the common words that do not contribute much meaning to the text chunk. For example, converting the quick brown fox jumps over the lazy dog to quick brown fox jumps lazy dog. An embedding function that converts text to numerical vectors. This function is used to convert each text chunk into a numerical vector representation. The embedding function can be a pre-trained model like sentence transformers, OpenAI embeddings, or custom trained model. Sentence transformers is a library of pre-trained models for sentence embedding. Sentence transformers models can be used to embed text chunks into numerical vectors. For example, we can use the sentence transformers model OpenNetBase2 to embed the text chunk the quick brown fox jumps over the lazy dog into a numerical vector. OpenAI embeddings is a set of pre-trained models for text embedding. OpenAI embeddings models can be used to embed text chunks into numerical vectors. For example, we can use the OpenAI embeddings model TextEmbeddingAda002 to embed the text chunk the quick brown fox jumps over the lazy dog into a numerical vector. Fine-tune parameters. This component does not require fine-tuning. Challenges and fixes. High dimensionality of embedding vectors can lead to computational inefficiency. This is because calculating the cosine distance between two high-dimensional vectors can be computationally expensive. Use dimensionality reduction techniques e.g. PCA. Principal Component Analysis (PCA) is a dimensionality reduction technique that can be used to reduce the dimensionality of the embedding vectors. This can improve the computational efficiency of the cosine distance calculation. Memory constraints when calculating distances for large number of chunks. This is because storing the embedding vectors for a large number of text chunks can require a lot of memory. Use chunking or distributed computing. Chunking can be used to divide the text chunks into smaller groups. And then the cosine distances can be calculated for each group separately. Distributed computing can be used to calculate the cosine distances across multiple machines, which can reduce the memory requirements on each individual machine. Langchain experimental tools summary. These tools are still in the early stages of development and are considered experimental. They may not have the same level of polish or robustness as tools found in the main langchain library. Inputs. These tools accept instructions or prompts written in natural language. Users can express their requests or queries in a conversational way, making them more accessible for a wider range of users. Tools can also leverage contextual information to improve their responses. This information can be provided in various formats, such as text, code, or structured data. The tool can then utilize this context to understand the user's intent and provide more relevant and accurate outputs. Outputs. Tools can generate different types of outputs depending on their purpose and design. This can include structured data, such as tables, lists, or JSON objects, or unstructured data, such as text, code, or images. In addition to data outputs, these tools can also execute actions or generate responses based on the input they receive. For example, a tool might interact with an application programming interface API to retrieve information. Or it could generate a piece of code based on user input. Steps. The first step in using these tools is to provide them with input. This input can come from a user directly, or it can be passed from another component within a larger system. Once the input is received, the tool's logic processes it. This might involve parsing the input, analyzing its content, or applying specific algorithms or rules. Based on the processed input, the tool generates an output. This output could be in the form of structured or unstructured data, or it could be an action that is executed. Prerequisites. These tools require the installation of the LangChain library. Users can install it using the package manager pip. The command pip install langchain will download and install the necessary files. Before using these tools, users must have a Python environment set up. This involves installing Python itself, which can be downloaded from the official website. It's recommended to use Python version 3.8 or later for optimal compatibility and performance. Fine-tune parameters. These tools often have specific parameters that can be adjusted to fine-tune their functionality. This allows users to customize the tool's behavior for different tasks or applications. Configuration settings are used to optimize the performance of the tool. This might involve setting thresholds for specific calculations, adjusting the size of internal data structures, or specifying the resources the tool can access. Challenges and fixes. Since these tools are still under development, they might experience issues with stability or compatibility. It's important to be aware of potential problems and to regularly check for updates and bug fixes. Documentation and examples for these experimental tools might be limited at first. The community can contribute to the documentation by sharing their experiences and code examples. And developers will continually strive to improve the documentation. Summary of LangChain experimental tools. Python tool. Python inputs. A Python tool is a core element within the LangChain framework, designed to empower language models by extending their capabilities through interactions with external systems and data sources. These tools function by accepting input data, processing it using Python code, and returning the results. In essence, they provide a bridge between the language model's ability to understand and generate text and real-world actions that can be performed using Python. Inputs. Input arguments are the values passed to the tool for execution. They serve as the raw material that the tool operates on. For instance, in a weather tool, an input argument could be the city name for which the user wants to get weather information. Optional keyword arguments are additional parameters that can be used to refine the tool's behavior. They allow for more flexibility and control over how the tool operates. In the weather tool example, a keyword argument could be the unit of measurement for temperature Celsius or Fahrenheit. Outputs. The output represents the result of the tool's execution, delivered back to the language model. This could be any type of data that the Python code generates, such as text, numbers, lists, or even images. In the weather tool scenario, the output would be the weather information for the specified city, including temperature, humidity, and other relevant details. Exceptions are unexpected errors that occur during the tool's execution. These can arise from various issues like incorrect inputs, network problems, or bugs within the tool's code. When an exception occurs, the tool will typically report it to the language model, providing insights into the reason for the error. Steps. The tool receives the inputs and keyword arguments provided by the language model. This phase involves passing the data received from the language model to the tool's internal Python code for processing. The tool's Python code is executed with the received inputs and keyword arguments. This is the core step where the actual processing happens, leveraging the power of Python to perform operations based on the provided data. The tool returns both the output generated by the Python code and any exceptions encountered during execution. This feedback loop ensures that the language model is aware of both the successful outcome and any potential issues that arose during the process. Prerequisites. A Python interpreter, the foundation of Python programming, is required to execute the tool's code. It serves as the runtime environment that interprets and executes the Python instructions within the tool. A specific version of Python, typically 3.7 or later, is often required to ensure compatibility with the libraries and features used in the tool's code. The tool relies on a set of Python libraries, which are collections of pre-written code that provide various functionalities. LangChain, a powerful framework for building language-based applications, is a crucial dependency, enabling the tool to interact with other components within the LangChain ecosystem. Additionally, other libraries specific to the tool's purpose might be required, such as libraries for data processing, networking, or interaction with external APIs. Fine-tune parameters. Tool code customization involves modifying the Python code within the tool to tailor its behavior to specific tasks. This process enables you to adapt the tool to handle specific input formats, perform customized calculations, or interact with unique external systems. For example, you might adjust the code to handle financial data, parse specific website structures, or interact with a particular application programming interface API. Configuration of the tool's behavior involves specifying settings and parameters that control how the tool operates. These settings can be used to define input and output formats, manage resource allocation, and set thresholds for error handling. For instance, you might configure the tool to handle a specific number of requests concurrently, set time limits for execution, or define error recovery mechanisms. Challenges and fixes. Code errors, unexpected inputs, or library incompatibilities are common challenges that can arise when working with Python tools. Code errors occur when there are syntax mistakes or logical flaws in the tool's code. Unexpected inputs can occur when the tool receives data that is not in the expected format or range, causing unexpected behavior. Library incompatibilities arise when the tool relies on libraries that are not properly installed or have conflicting versions, leading to errors during execution. Debugging the code involves systematically identifying and fixing errors, using tools like debuggers and logging to trace the execution flow. Handling exceptions involves gracefully managing errors by catching them and taking appropriate actions, such as providing informative error messages or attempting to recover from the error. Updating dependencies ensures that the tool uses the latest versions of libraries, which can address security vulnerabilities and improve performance. Integration with other LangChain components involves connecting the Python tool to other elements within the LangChain framework, such as language models, chains, and memory modules. This allows for creating complex workflows and building sophisticated language-based applications. Tool limitations refer to inherent constraints in the tool's capabilities, such as limitations in processing speed, data handling capacity, or the scope of external systems it can interact with. Adjusting the tool interface involves modifying how the tool interacts with other components, such as changing the input and output formats or adding new functionality. Exploring alternative solutions involves considering different approaches to address limitations, such as using alternative tools, libraries, or methods to achieve the desired outcome. Langchain experimental tools, Python tool, Python input summary. A class that defines the inputs required for a Python tool. This class serves as a blueprint for defining the necessary parameters for executing a Python function as a tool. Inputs, arguments to be passed to the Python function. These are positional arguments that are passed in the order they are defined in the function. Signature. For example, if the function signature is def my function arg1, arg2, then the arguments would be r1 and r2. Keyword arguments to be passed to the Python function. These are arguments that are passed by name, and their order does not matter. For example, if the function signature is def my function arg1, arg2, then the keyword arguments could be r1 value 1 and r2 value 2. Outputs. The result generated by the execution of the Python function. This output represents the return value of the function, which could be any data type supported by Python, such as a string, a number, a list, or a dictionary. Steps. The Python function is invoked with the provided arguments and keyword arguments. The function execution takes place within the specified Python environment, ensuring that the necessary dependencies and packages are available. The output generated by the Python function is returned as the result of the tool execution. This output represents the outcome of the function execution and can be used in subsequent steps or processed further as needed. Prerequisites. A Python function that accepts the specified inputs and performs the desired operation. This function should be defined and available within the Python environment. For example, a function to calculate the sum of two numbers could be defined as Python def sum numbers x, y, return xy. A Python environment that includes the necessary packages and libraries required for the Python function to execute successfully. This environment should be configured and accessible to the tool. For example, if the function uses the NumPy library for numerical calculations, the Python environment should have NumPy installed. Fine-tune parameters. The Python function to be executed as the tool. This parameter defines the specific function to be called within the tool. The function should be defined and available within the Python environment. The name of the tool, which is used to identify the tool and differentiate it from other tools. A description of the tool, providing a clear explanation of the tool's purpose and functionality. This description helps users understand what the tool does and how to use it. The positional arguments to be passed to the Python function. These arguments are defined in the tool configuration and are used as inputs to the function during execution. The keyword arguments to be passed to the Python function. These arguments are defined by name in the tool configuration and are used as inputs to the function during execution. Challenges and fixes. Function error. The Python function may encounter an error during execution, such as a division by zero, a type mismatch, or an invalid input. To handle such errors, the tool should implement error handling mechanisms. This can involve catching exceptions raised by the function and providing informative error messages to the user. For example, if the function attempts to divide by zero, The tool could catch the zero division error exception and return an error message indicating that the operation cannot be performed. Incorrect inputs. The inputs provided to the Python function may not be valid or may not match the expected types. To prevent such issues, the tool should validate the inputs before calling the function. This validation can involve checking the data types, ranges, or formats of the inputs. For example, if the function expects an integer input, the tool could check if the input provided is indeed an integer before passing it to the function. Unexpected output. The output generated by the Python function may be unexpected or may not match the expected data type. To handle such situations, the tool should implement mechanisms to handle unexpected output types. This could involve checking the type of the output and converting it to the expected type if necessary. For example, if the function is expected to return a string, but it returns a list of strings, the tool could convert the list to a string by concatenating its elements. LangChain experimental tools. Python tool. Python input summarization. None. The Python inputs class represents the inputs for a Python tool. It provides a structured way to define and manage the inputs of a Python tool. Inputs. A list of positional arguments passed to the tool. For example, if the Python tool is a function that takes two arguments, a and b, then the args input would be a list containing a and b. A dictionary of keyword arguments passed to the tool. For example, if the Python tool is a function that takes two arguments, a and b, then the quargs input would be a dictionary containing the keys a and b and their corresponding values. Outputs. The output generated by the tool. This could be any type of data, such as a string, a list, a dictionary, or a custom object. Steps. Initialize the Python inputs object with the required inputs. This involves providing the args and quargs values to the Python inputs constructor. Pass the Python inputs object to the Python tool as an argument. This allows the tool to access the input values provided in the Python inputs object. Prerequisites. Import the necessary libraries for the Python tool. For example, if the tool uses the requests library to make API calls, then you will need to import the requests library. The LangChain library provides a framework for interacting with tools, including Python tools. It allows you to define tools, manage their inputs and outputs, and integrate them into larger workflows. Define the Python tool function. This is the function that will be executed by the tool. It should accept the Python inputs object as an argument, which will allow it to access the input values provided to the tool. Fine-tune parameters. Customize the positional arguments passed to the tool. This allows you to adjust the behavior of the tool by modifying the values of the positional arguments. Modify the keyword arguments passed to the tool. This allows you to adjust the behavior of the tool by modifying the values of the keyword arguments. Challenges and fixes. The tool might not accept the expected input format. For example, the tool might expect a specific data type for an input, but the input provided might be of a different type. Ensure that the inputs are provided in the correct format. This might involve converting the input data to the expected type, or providing the input data in a specific structure. The tool might not return the desired output. For example, the tool might return an error message instead of the expected output, or it might return an empty output. Review the tool's implementation and make necessary adjustments. This might involve debugging the tool's code, or modifying the input data or the tool's logic to ensure that it produces the desired output. LangChain experimental, text splitter, semantic chunker. The semantic chunker class is a component of the LangChain framework. A powerful tool for working with large language models (LLMs), its primary function is to divide text into coherent and meaningful sections based on semantic relationships within the text. This approach contrasts with simpler chunking methods that simply split the text into equal-sized segments, potentially disrupting natural coherence. Inputs: the text that needs to be divided into semantically relevant chunks. This could be a document, an article, or any other substantial piece of written content. An instance of a base LLM class from the LangChain library. This LLM is used to generate embeddings for each token in the text. Embeddings are numerical representations of words or phrases that capture their semantic meaning, facilitating comparison and clustering. Outputs: a list of text chunks. These chunks represent meaningful segments of the input text that have been identified by a semantic chunker. Each chunk is a self-contained unit of information, preserving the semantic integrity of the original text. Steps: 1. Tokenize the input text. This step involves breaking down the input text into individual tokens, which are the basic units of language. Tokens can be words, punctuation marks, or other meaningful units. 2. Use the LLM to generate embeddings for each token. The LLM takes each token and generates a numerical embedding that captures its semantic meaning. This is crucial for the subsequent clustering process. 3. Cluster the tokens based on their embeddings. The embeddings generated by the LLM are used to group tokens into clusters based on their semantic similarity. Tokens with similar meanings tend to be grouped together. 4. Group the tokens into chunks based on the clusters. Finally, the clusters of tokens are used to create the chunks of text. Tokens within a cluster are grouped together to form a coherent and semantically meaningful chunk. Prerequisites: a base LLM instance from LangChain. This is the core component responsible for generating embeddings. OpenAI's Text DaVinci 003, a powerful text-based LLM from OpenAI's suite of language models, known for its advanced capabilities. This specific model is particularly well suited for generating high-quality embeddings. Google's Text Bison. This is a text-based LLM from Google, known for its strong performance and ability to handle diverse tasks. It can effectively generate embeddings for various text input types. A base embedding instance from LangChain. This component is responsible for calculating embeddings of tokens. OpenAI's Text Embedding ADA 002. This is a specialized embedding model from OpenAI that is optimized for generating embeddings for textual data. It is widely used for tasks involving semantic similarity and clustering. Google's Text Embedding ADA 002, a comparable embedding model from Google, also optimized for generating high-quality text embeddings. This model is often used in tasks where accurate semantic representation is crucial. Fine-tune parameters. Chunk size. This parameter controls the desired size of each chunk. It defines the approximate number of tokens that should be included in a single chunk. Chunk overlap. This parameter determines the number of tokens that should overlap between consecutive chunks. This overlap helps to ensure a smooth transition between chunks and prevents information loss at the boundaries. Challenges and fixes. The LLM may not be able to identify all semantic boundaries. This can occur if the text is complex or contains subtle semantic shifts that are difficult for the LLM to detect. Increase the chunk size or chunk overlap. This approach increases the size of each chunk and degree of overlap between chunks, potentially improving the LLM's ability to capture semantic boundaries. The LLM may not be able to identify all semantic boundaries in some cases. The LLM's capabilities may be insufficient to accurately detect all semantic shifts in the text. Try using a different LLM or embedding model. This can be helpful if the current LLM is struggling to identify semantic boundaries. Experimenting with different LLMs and embedding models can lead to better results. LangChain Experimental Tools Summary. Collection of experimental tools designed for extending LangChain functionality, offering various features such as enhanced data access, custom integrations, and experimental capabilities. Inputs. The input to the LangChain Experimental Tools Summary is a user query or question. Outputs. The output of the LangChain Experimental Tools Summary is a response that is generated by the tools. Steps. Initialize LangChain with the desired tools and models. This involves specifying the tools and models that you want to use. Construct the prompt that incorporates the tools. The prompt should be designed in a way that guides the tools to provide a helpful and relevant response. Execute the prompt using LangChain's run method. This will execute the tools and generate a response. Retrieve and process the tool-generated response. This step involves extracting the relevant information from the response and presenting it in a user-friendly format. Prerequisites. Python environment 3.7 or later. This is the minimum required version of Python to run LangChain. LangChain library installed via pip. This is the primary library used for building and running LangChain applications. Fine-tune parameters. Tool arguments. These are the parameters that are passed to the tools. These parameters can be used to customize the behavior of the tools. Model parameters. These are the parameters that are passed to the language models. These parameters can be used to control the behavior of the language models. Prompt engineering. This refers to the process of designing effective prompts that guide the tools and models to generate accurate and helpful responses. Challenges and fixes. Tool integration issues. Ensure compatibility and proper configuration. This involves ensuring that the tools are compatible with LangChain and that they are properly configured. Output parsing difficulties. Define clear output formats and use appropriate parsing techniques. This involves ensuring that the output from the tools is in a format that can be easily parsed and processed. Tool execution failures. Handle potential errors and provide user-friendly feedback. This involves handling errors that may occur during tool execution and providing clear feedback to the user. Unexpected behavior. Debug issues systematically and test extensively. This involves identifying and resolving unexpected behavior by carefully debugging the code and testing the application thoroughly. LangChain Experimental Tote. A description of the tool orchestration toolkit. Tote, which is a framework for coordinating and managing various tools to perform complex tasks. This toolkit essentially acts as a central hub for orchestrating diverse tools, allowing for seamless integration and collaborative work. Inputs. A list of tools that the tote will utilize in its operations. This list could include various tools such as application programming interfaces (APIs), databases, document processors, and other relevant software components. An input prompt or query that triggers the tote's workflow. The prompt defines the desired outcome and provides context to the toolkit for selecting appropriate tools and executing them. Outputs. The final output generated by the tote, which is a consolidated result derived from the execution of all the tools involved in the workflow. This output could take various forms based on the nature of the task and the tools used, such as a textual summary, a structured data representation, or a multimedia file. Steps. The process of identifying suitable tools based on the input prompt. This step involves analyzing the prompt, determining the required actions, and selecting the most relevant tools from the available pool. The execution of selected tools based on the identified tasks and their corresponding input parameters. This step involves calling the tools, providing them with the necessary data, and receiving their outputs. The combination of individual outputs from each tool into a unified and coherent output. This step involves consolidating the results from different tools, aligning them to a common format, and presenting them as a comprehensive answer to the input prompt. Prerequisites. LangChain, a powerful library that provides a foundation for building and deploying language-based applications. It offers various functionalities including chain composition, memory management, and integration with external tools. Tools that will be orchestrated by the tote. These tools could be external services, APIs, or custom-built components that perform specific tasks. For example, a summarization tool could be used for extracting key information from a document. A translation tool could be employed for translating text between languages. And a data analysis tool could be used for extracting insights from a dataset. Fine-tune parameters. The logic used for selecting tools based on the input prompt. This parameter determines the strategy for identifying the most suitable tools from the available set. For example, a rule-based approach could be used where predefined rules map specific prompt keywords to corresponding tools. Alternatively, a machine learning model could be trained to learn the relationship between prompts and tools, enabling more dynamic selection. The method used to aggregate the outputs from different tools. This parameter defines how the individual results are combined into a unified output. Techniques could include simple concatenation, weighted averaging, or more sophisticated methods that consider the context and relevance of each output. Challenges and fixes. Challenges that arise from potential incompatibilities between different tools in terms of their input and output formats, data structures, or communication protocols. Utilizing adapters to bridge the gap between incompatible tools. Adapters act as intermediaries that translate data between different formats and protocols, ensuring seamless communication and integration between tools. Challenges that arise from potential errors during tool execution. These errors could be due to network issues, invalid input parameters, or unexpected behavior from the tool itself. Implementing error handling mechanisms to gracefully handle exceptions. Log errors for debugging purposes. And provide alternative solutions or fallback strategies in case of tool failures. Challenges that arise from merging outputs from different tools into a coherent and unified output. This can be challenging when outputs are in diverse formats, contain conflicting information, or require specific ordering and structuring. Utilizing consistent output formats across different tools to facilitate easier merging and integration. This could involve standardizing data structures, using specific output templates, or employing dedicated merging algorithms that handle data discrepancies. Challenges that arise from the order in which tools are executed. The order of execution can significantly impact the overall outcome, particularly when tools depend on the outputs of other tools. Prioritizing essential tools that provide foundational information or outputs. Ensuring that these tools are executed before dependent tools. This prioritization helps avoid dependency issues and ensures that subsequent tools have necessary inputs for successful execution. Summary of LangChain experimental tools. Python tool. Python inputs. A tool that allows you to execute Python code. This tool is designed to enable LangChain agents to interact with and utilize Python code as part of their workflows. Inputs: a string representing the Python code to be executed. This string can contain any valid Python code, including functions, classes, and complex logic. For example, this input might be print hello world, or def addx y and return x y and print add 2. 3. Outputs: the output of the Python code execution. This output could be anything that the executed code produces, such as printed text, calculated values, or data structures. For example, the output might be hello world, or 5 steps. 1. The tool receives the Python code as input. The tool first takes the Python code string as input, processing it to understand the instructions it contains. 2. The tool executes the Python code. The tool then uses the Python interpreter to execute the received code, processing it line by line and performing the actions specified. 3. The tool returns the output of the code execution. Once the code has been executed, the tool captures the output generated by the code and returns it to the calling agent, providing the results of the executed Python logic. Prerequisites: Python installed and available in the execution environment. This implies that the environment where this tool is used must have a working Python installation available to run the provided code. The Python code provided as input must be valid and executable. The code should adhere to Python syntax rules and be free of errors to ensure proper execution. This means the tool should be able to parse and understand the code before attempting to run it. Fine-tune parameters: none. This tool does not require any specific fine-tuning parameters to be set. It functions based on the provided Python code and the standard Python environment. Challenges and fixes. Challenge 1: Python code execution errors. Python code can contain errors that prevent it from executing correctly. For example, syntax errors, undefined variables, or invalid function calls can cause the code to fail. Fixes to challenge 1: ensure the Python code is valid and well-formed, and handle potential errors gracefully. To address this challenge, the tool should implement error handling mechanisms. This involves detecting potential errors, providing informative messages about the cause of the error, and allowing for graceful recovery or alternative actions to be taken. Error handling can be implemented through exception handling mechanisms in Python. Challenge 2: the Python code requires external dependencies. Python code often relies on external libraries or packages to perform specific tasks. For example, a code snippet might use the requests library to make HTTP requests or the pandas library for data analysis. Fixes to challenge 2: install the required dependencies before executing the code. The tool should be able to detect the required dependencies and install them automatically before executing the code. This can be achieved using package managers like pip to install the necessary libraries. Challenge 3: the Python code takes a long time to execute. Python code can contain complex computations or operations that require significant processing time. For example, data processing tasks, simulations, or machine learning models might require considerable resources and execution time. Fixes to challenge 3: consider optimizing the code or using a timeout mechanism to prevent execution from hanging. Optimizing the code by using efficient algorithms, data structures, and avoiding unnecessary computations can help reduce execution time. Additionally, a timeout mechanism can be implemented to prevent the code from running indefinitely and potentially blocking the agent's workflow. Challenge 4: the Python code interacts with external systems, e.g., Databases. Application programming interfaces. Python code can interact with various external systems like databases, application programming interfaces (APIs), and web services to access data, send requests, or retrieve information. For instance, code might query a database for specific information or send requests to a web API to get data from an external service. Fixes to challenge for ensure appropriate authentication and authorization mechanisms are in place. For these interactions, secure access to external systems requires proper authentication and authorization measures. This can involve providing user credentials, API keys, or tokens to authenticate with the target systems and ensure that only authorized actions are performed. Challenge 5. The Python code requires access to sensitive data. Python code might need to access sensitive data such as user information, financial data, or proprietary business data. Fixes to challenge 5 implement robust security measures to protect sensitive data, such as data encryption and access control. Secure handling of sensitive data is crucial. This involves using data encryption techniques to protect data at rest and in transit. Access control mechanisms should be implemented to restrict access to sensitive data to authorized users and prevent unauthorized access or modification. Challenge 6. The Python code generates output that needs to be formatted or processed further. The output generated by Python code may not be in the desired format or might require additional processing before it can be used by the agent. For example, a code snippet might return data in a raw format that needs to be converted to a specific format or processed to extract specific information. Fixes to challenge 6. Implement appropriate formatting and processing logic within the tool or in downstream components. The tool should be able to handle different output formats and provide mechanisms for processing and transforming the output according to the requirements of the agent's workflow. This can involve using libraries for data manipulation, text formatting, or data serialization deserialization to convert the output to the desired format. Langchain experimental total summary. Langchain experimental total orchestration summary total is a feature that provides a unified interface for orchestrating multiple tools and chains. This allows for the creation of complex workflows that can be easily managed and reused. Inputs: a list of tools and chains that will be used in the orchestration. For example, you may want to use a tool to access a database, a chain to process natural language, and another tool to generate images. A set of parameters that will be used to configure the orchestration. These parameters can be used to specify the order in which the tools and chains are executed, the inputs and outputs of each tool and chain, and other settings. Outputs: the output of the orchestration. This can be anything from a simple string to a complex data structure. Steps: define the tools and chains that will be used in the orchestration. This involves specifying the type of each tool and chain, as well as any necessary parameters. Configure the parameters of the orchestration. This involves specifying the order in which the tools and chains will be executed, the inputs and outputs of each tool and chain, and other settings. Execute the orchestration using the specified tools and chains. This involves running the tools and chains in the specified order, passing the outputs of each tool or chain as inputs to the next one. Prerequisites: LangChain library installed. This can be achieved by running the following command in your terminal: pip install langchain. Tools and chains that will be used in the orchestration defined. These tools and chains can be defined using the langchain library, or they can be imported from other libraries. Fine-tune parameters. Tools: a list of tools and chains to be used in the orchestration. Each tool or chain can be defined using a dictionary that specifies its type and any necessary parameters. Chain type: the type of chain to be used for the orchestration. The chain type determines the way in which the tools and chains are executed. Challenges and fixes: difficult to manage complex orchestrations with multiple tools and chains. This can be overcome by using a structured approach to define tools and chains, such as creating a separate file for each tool or chain and using a configuration file to specify the order in which they are executed. Difficult to debug complex orchestrations. This can be overcome by using logging and tracing to track the execution of the orchestration. Logging can be used to record the inputs and outputs of each tool and chain, while tracing can be used to track the flow of data through the orchestration. Langchain experimental prompts: checker, output, parser, summary. Inputs: prompt: the input prompt to the language model or another prompt-based tool that takes in a user prompt and produces some output. This is a core piece of a language model application. Output: the output from the language model or other prompt-based tool. Output is what the model or tool returns in response to the user prompt. In general, this is text. Outputs: check result: this is the result of checking the output of a language model. The checker, a separate piece of software specifically built to check the output, returns a result that indicates whether the output meets the intended goal. Steps: create a checker from prompt and output. The checker is a specialized tool that checks the output of a language model or other prompt-based tool. The checker needs to be set up or configured with a specific input prompt and the desired output. This step creates a checker for a specific prompt-on-output combination. Run the checker on the output. This is where the checker analyzes the output and determines if it meets the requirements set in the checker. For example, it might check that the output is a well-formed sentence, or that it adheres to a specific format. Prerequisites: Langchain Experimental. This is a Python library that provides an experimental toolkit for building and deploying language models. It is a key prerequisite for this particular checker output parser. Prompts: this is another Python library designed to work with the LangChain library, specifically for creating and working with prompts. It is specifically used for building prompts for use with language models. Fine-tune parameters. Threshold: this is a numerical value that sets a level of strictness in the checker. For example, if the check function is measuring the similarity between the output and a desired output, the threshold can define the level of similarity required for the output to pass. A lower threshold means that the checker will be more tolerant of variations, while a higher threshold means that the checker will be more strict. Check function: this defines the specific logic or algorithm that the checker will use to assess the output. A check function might compare the output to a specific expected output, measure the output against a set of rules or constraints, or perform other kinds of checks. Challenges and fixes. Unable to find matching output in the checker. Use different check function. The checker might not be able to find a match for the output, potentially because the output does not meet the expectations set in the checker. One possible solution is to modify the check function so that it has a broader definition of what constitutes a successful output. For example, if the check function is currently looking for a specific phrase in the output, it could be modified to accept synonyms or other variations. Checker is too strict. Lower the threshold if the checker is marking too many outputs as failures. It might be too strict. This is a common problem when a check function has a high threshold for acceptance. To remedy this, the threshold can be lowered. making the checker more tolerant of minor variations or differences. Summary of LangChain experimental taught prompts checker output parser. Inputs. The input to the checker output parser is a combination of a prompt and a checker. A prompt is a text input that is provided to the checker for evaluation. A checker is a function or a class that evaluates the prompt based on predefined criteria. For example, a prompt could be a question, and the checker could be a function that checks if the question is grammatically correct and meaningful. Outputs. The output of the checker output parser is the output from the checker. This output could be a Boolean value indicating whether the prompt passed the evaluation, or it could be a more detailed report, depending on the checker's implementation. Steps. The checker output parser first extracts the prompt and the checker from the input. This step involves parsing the input to identify the prompt and the checker. The checker output parser then runs the checker on the prompt. This step involves executing the checker function or class with the prompt as input. Finally, the checker output parser returns the checker's output. This step involves returning the output produced by the checker after running the checker on pay. Prompt. Prerequisites. The checker output parser requires a checker to be defined before it can be used. A checker can either be a LangChain checker, which is a pre-built checker provided by the LangChain library, or a custom checker, which is a user-defined function or class that implements the checker logic. The checker output parser also requires a valid prompt to be provided. A valid prompt is one that meets the requirements of the checker. For instance, if the checker is designed to evaluate questions, a valid prompt would be a well-formed question. Fine-tune parameters. The checker output parser can be fine-tuned with checker-specific parameters. These parameters are used to control the behavior of the checker during the evaluation process. For example, a checker that evaluates text for sentiment might have a parameter to adjust the threshold for classifying text as positive or negative. Challenges and fixes. If the checker is not defined, the checker output parser will not be able to evaluate the prompt. To fix this issue, the checker needs to be defined before using the checker output parser. This involves providing the checker output parser with a valid checker definition. If an invalid prompt is provided, the checker output parser might not be able to run the checker or produce a meaningful output. To fix this issue, a valid prompt should be provided to the checker output parser. This involves ensuring that the prompt meets the requirements of the checker. If the checker fails to run, it might be due to issues with the checker's implementation or missing dependencies. To fix this issue, the checker's implementation needs to be checked for errors, and any missing dependencies need to be installed. This involves verifying the code of the checker and ensuring that it is correctly written and that all necessary libraries are available. Summary of LangChain experimental taught prompts JS on list output parser. Description of inputs. These are the prompts provided to the language model. They serve as instructions or questions for the model to generate responses to. These prompts can be in the form of text, code, or any other format that the language model can understand. For example, if the task is to summarize a news article, the input prompt could be the text of the news article. The output format specifies how the language model should structure its responses. This can include formats like plain text, JSON, or CSV. The choice of output format depends on the intended use of the generated responses. For example, if the output needs to be processed by a specific application programming interface API or tool, the output format should be compatible with that API or tool. Description of outputs. This represents a list of objects structured in JSON format. Each object contains a set of key-value pairs, representing structured data. This output format is commonly used for storing and exchanging data between different systems and applications. For example, a list of JSON objects could represent a collection of customer records, each containing information like name, address, and contact details. This is a collection of textual responses generated by the language model. Each string represents a separate piece of text, such as a paragraph, a sentence, or even a single word. This output format is suitable for tasks that require text generation, such as writing summaries, stories, or poems. Description of steps. This involves interpreting the responses from the language model according to the specified output format. This step ensures that the output is in a structured and understandable form. For example, if the output format is JSON, this step would pass the language model's output into a valid JSON structure. This step converts the parsed output into a format that can be easily processed by other tools or applications. The JSONList output parser is a specific tool used in this context to handle outputs that are lists of JSON objects. This step allows for further analysis, manipulation, or use of the generated responses. Description of prerequisites. The language model must be capable of processing the provided input. This means that the model should have been trained on data similar to the input format and be able to understand the context of the input. If the input is in a format the model is not familiar with, it may not produce meaningful or accurate outputs. The output format must be compatible with the capabilities of the language model. Some models may be better suited for generating text in certain formats, such as plain text or JSON, while others may be more proficient at generating code. If the output format is not compatible with the model's capabilities, it may lead to unexpected or incorrect results. Description of fine-tune parameters. This parameter controls the number of responses that the language model generates for a given prompt. By adjusting this value, you can control the number of outputs produced. For example, if you want multiple summaries of a news article, you would increase the number of outputs to generate. This parameter specifies the structure and format of the JSON objects that the language model generates. This includes the types of data that should be included in each object and the names of corresponding keys. By defining the output format for JSON objects, you ensure that the generated responses are consistent and easily interpretable. Description of challenges and fixes. The language model may not be able to correctly interpret the output format and produce the desired results. This can occur if the model is not familiar with the specific format or if the output format is complex. This issue can be addressed by selecting a language model that is better suited for the task or by fine-tuning the current model on data that includes the desired output format. Fine-tuning involves training the model on a specific dataset to improve its performance on a particular task or format. The output format may be incompatible with the JSONList output parser, leading to errors or unexpected behavior. This can happen if the output format is not structured correctly or if it contains data types that the parser does not support. This challenge can be overcome by modifying the output format to make it compatible with the JSONList output parser. Alternatively, you can use a different output parser that is better suited for the generated output format. This involves choosing an output parser that can handle the specific data Types and structure of the language. Models output. langchainexperimental. Controller. To T controller. A controller for tree of thoughts tot reasoning. It helps to generate multiple hypotheses and refine them iteratively to get a final answer. For example, if you want to answer the question what is the capital of France? The tot controller would first generate multiple hypotheses, such as Paris, London, Berlin. Then, it would use a tot reasoner to refine these hypotheses by evaluating them against the question and other relevant information. Finally, it would select the most likely answer, which in this case would be Paris. Inputs. A prompt that is used to generate tot. This prompt should be carefully crafted to ensure that the tot controller can generate relevant and informative hypotheses. For example, the prompt "What is the capital of France?" would be suitable for generating hypotheses about the capital of France. Outputs. A final answer that is the most likely based on the tot. The final answer should be a concise and accurate answer to the question posed in the prompt. For example, the final answer to the prompt "What is the capital of France?" would be Paris. Steps. Generate multiple hypotheses using the provided prompt. This step involves using a language model to generate multiple possible answers to the question posed in the prompt. The number of hypotheses generated can be adjusted according to the complexity of the question and the desired level of confidence in the final answer. Use a tot reasoner to refine the hypotheses. This step involves using a tot reasoner to evaluate the generated hypotheses against the prompt and other relevant information. The tot reasoner will typically use a combination of logic, reasoning, and common sense to refine the hypotheses and identify the most likely answer. Select the most likely answer based on the refined hypotheses. This step involves analyzing the refined hypotheses and selecting the one that is most likely to be correct based on the evidence provided. The final answer should be a concise and accurate answer to the question posed in the prompt. Prerequisites. A prompt that is suitable for tot reasoning. The prompt should be clear, concise, and well defined. It should also be relevant to the task at hand and should provide enough information for the tot controller to generate informative hypotheses. A tot reasoner that can refine the hypotheses. The tot reasoner should be capable of using logic, reasoning, and common sense to evaluate the generated hypotheses and identify the most likely answer. It should also be able to access and process relevant information from external sources, such as knowledge bases or databases. Fine-tune parameters. The number of hypotheses to generate. This parameter controls the number of hypotheses that are generated in the first step of the tot process. Increasing the number of hypotheses can increase the accuracy of the final answer, but it can also increase the computational cost of the process. The number of steps to refine the hypotheses. This parameter controls the number of steps that are used to refine the generated hypotheses. Increasing the number of steps can increase the accuracy of the final answer, but it can also increase the computational cost of the process. Challenges and fixes. The tot reasoner might not be able to refine the hypotheses effectively. This could be due to a number of factors, such as the complexity of the question, the quality of the tot reasoner, or the availability of relevant information. Use a different tot reasoner. If the current tot reasoner is not performing well, try using a different one that is better suited to the task at hand. The final answer might not be accurate. This could be due to a number of factors, such as errors in the generated hypotheses, limitations in the tot reasoner, or lack of relevant information. Increase the number of hypotheses to generate. Increasing the number of hypotheses can increase the likelihood that the final answer is accurate. Increase the number of steps to refine the hypotheses. Increasing the number of steps can increase the likelihood that the final answer is accurate. Langchain experimental. Thought generation. Base thought generation strategy. A base class for thought generation strategies in Tote Tree of Thoughts. This class provides a blueprint for strategies that generate new thoughts within the context of a Tote, a hierarchical structure used for organizing and exploring potential solutions to complex problems. The base thought generation strategy class establishes a standard framework for all thought generation strategies, ensuring consistency and facilitating modularity within Tote. Inputs. The current node in the thought tree. This input refers to the specific position within the Tote structure where the thought generation process takes place. It provides the context and relevant information associated with the current stage of exploration. The current state of the Tote. This input represents the overall status and progress of the Tote at the time of thought generation. It encompasses factors such as previously explored paths, constraints, and accumulated knowledge. Outputs. A list of possible next thoughts. The output of a thought generation strategy is a collection of potential next steps to explore. Within the Tote, these thoughts may represent various approaches, ideas, or actions to be considered based on the current context and previous explorations. Steps. Initialize the strategy with the current node and state. This step involves providing the strategy with the necessary information about the current position and overall progress within the Tote. The strategy then prepares itself to generate relevant thoughts based on this context. Generate a list of possible next thoughts. This is the core step where the strategy utilizes its defined logic and parameters to generate a list of potential next steps to explore. The specific methods used for generating thoughts vary depending on the chosen strategy. Return the generated thoughts. The final step involves returning the list of generated thoughts to the Tote system, allowing it to proceed with exploring the proposed next steps. Prerequisites. An initialized Tote object. A fully initialized Tote object is essential for the thought generation strategy to function correctly. The Tote object provides the structural foundation and relevant information for the strategy to operate within. Fine-tune parameters. None. The base thought generation strategy class itself does not offer any fine-tuning parameters. Fine-tuning is typically handled by specific implementations that inherit from this base class. Challenges and fixes. The strategy may generate too many or too few thoughts. Adjust the strategy's parameters or use a different strategy. If the strategy generates too many thoughts, it may overwhelm the Tote with options, slowing down the exploration process. Adjusting parameters, such as the number of thoughts to generate, or switching to a more focused strategy can address this issue. Conversely, if the strategy generates too few thoughts, it may limit exploration and miss potentially valuable paths. Similarly, modifying parameters or using a more comprehensive strategy can help address this challenge. The strategy may generate irrelevant or redundant thoughts. Improve the strategy's logic or use a different strategy. Generating irrelevant thoughts leads to wasted time and effort exploring paths that are unlikely to lead to a solution. Improving the strategy's logic, such as incorporating domain knowledge or filtering based on relevance, can help address this issue. Redundant thoughts can also slow down exploration by repeating already explored paths. Using a strategy that avoids repetition or employs techniques to identify and eliminate redundant thoughts is crucial. Maintaining coherence. This challenge arises when the LLM generates thoughts that deviate from the intended conversation flow or lack a logical connection to the previous thoughts. To address this, fine-tuning the temperature and top K parameters can help achieve better coherence by controlling the randomness and diversity of the LLM's output, generating consistent actions. This challenge involves ensuring the LLM's generated actions are relevant to the ongoing conversation and aligned with the overall goals. Improving the action selection logic, including incorporating context awareness and goal alignment, can help mitigate this challenge. Langchain experimental thought generation sample quote strategy. A strategy for generating thoughts using a language model. This strategy leverages the power of large language models to assist in brainstorming, problem solving, or generating creative content. The goal is to use the model's ability to process and understand information to generate meaningful and relevant thoughts that can be further analyzed and developed. Inputs. A prompt that describes the task or problem. The prompt should be clear, concise, and specific, providing the language model with the necessary context and instructions to generate relevant thoughts. For example, a prompt could be generate 3 ideas for a new product that uses artificial intelligence. A language model. This refers to a language model like GPT-3 or similar, capable of understanding and generating human-like text. The model should have been trained on a massive dataset of text and code, enabling it to understand the nuances of language and generate coherent and relevant thoughts. Outputs. A list of thoughts generated by the language model. The output will be a collection of thoughts related to the given prompt, representing the model's understanding and creative interpretation of the task or problem. These thoughts can be used as a starting point for further exploration, discussion, or development. Steps. The prompt is passed to the language model. This step involves sending the user-defined prompt to the chosen language model via its application programming interface API or using a library designed for interacting with language models. The language model generates a list of thoughts. Once the prompt is received, the language model processes it, analyzes its meaning, and generates a list of thoughts based on its understanding and knowledge. This process involves utilizing its training data and internal mechanisms to produce relevant and creative ideas. Prerequisites. A language model capable of generating text. This refers to a language model like GPT-3, BARD, or similar, capable of understanding and generating human-like text. The model should have been trained on a massive dataset of text and code, enabling it to understand the nuances of language and generate coherent and relevant thoughts. A prompt that describes the task or problem. The prompt should be clear, concise, and specific, providing the language model with the necessary context and instructions to generate relevant thoughts. For example, a prompt could be generate 3 ideas for a new product that uses artificial intelligence. Fine-tune parameters. The temperature parameter of the language model. This parameter controls the randomness and creativity of the generated thoughts. A higher temperature leads to more unpredictable and potentially nonsensical outputs, while a lower temperature results in more predictable and potentially less creative outputs. The optimal temperature value depends on the specific task and the desired outcome. The top K parameter of the language model. This parameter controls the number of possible next words considered by the language model during text generation. A higher top K value increases the diversity of generated thoughts, potentially leading to more unexpected and unique results. Conversely, a lower top K value limits the number of potential words, resulting in more predictable and potentially less diverse outputs. The optimal top K value depends on the specific task and the desired outcome. Challenges and fixes. The language model may generate irrelevant or nonsensical thoughts. This can occur when the prompt is poorly defined, the language model is not adequately trained, or the model's parameters are not optimally configured. Adjust the temperature and top K parameters of the language model. Experiment with different parameter values to find the optimal settings for the specific task and desired outcome. Additionally, ensure that the prompt is well defined and provides sufficient context for the language model to generate relevant thoughts. The language model may generate repetitive thoughts. This can occur when the model is limited by its training data or when the prompt is not sufficiently specific or diverse. Use a different language model or adjust the prompt. Experiment with different language models or adjust the prompt to provide more specific instructions or different perspectives. This can help the model generate more diverse and original thoughts. langchainexperimental. Prompts.getCaught This YAML file describes the getCaught prompt function within the langchainexperimental. Prompts module. This function is designed to generate a chain of thought prompt for a given task, aiming to improve the reasoning capabilities of language models. Inputs. The task description provided to the function is a concise statement outlining the goal a language model should achieve. For instance, translate the following text into French or write a short story about a cat who loves to play piano. Input data refers to the specific content that the model will use to complete the task. This could be a text passage, a list of items, a dataset, or any other relevant information. Outputs. The output of this function is a chain of thought prompt. This type of prompt guides the language model to break down the task into a series of logical steps, effectively articulating its reasoning process. Steps. The initial step involves analyzing the provided task description and identifying the reasoning steps necessary to complete it. This could involve identifying key concepts, understanding relationships between elements, or determining the logical order of actions. The second step entails crafting a prompt that clearly outlines these identified reasoning steps. This prompt should guide the model through the reasoning process, prompting it to explicitly state its thought process and demonstrate its understanding of the task. Prerequisites. A fundamental understanding of chain of thought prompting is essential. This prompting technique relies on explicitly guiding language models to articulate their reasoning processes, which can enhance their accuracy and performance on tasks requiring logical thinking. Familiarity with the task and its specific requirements is crucial. The prompt needs to be tailored to the specific task, addressing its unique challenges and nuances. Fine-tune parameters. Prompt engineering skills are critical for creating effective chain of thought prompts. This involves carefully crafting prompts that are clear, concise, and effectively guide the model through the reasoning process. A deep understanding of the capabilities and limitations of the language model being used is essential. This allows for the creation of prompts that are appropriate for the model's abilities and avoid overly complex or unrealistic expectations. Challenges and fixes. One common challenge is creating prompts that are overly long or complex. This can overwhelm the model and hinder its ability to effectively reason. The solution lies in simplifying the prompt, breaking down complex instructions into smaller, more manageable steps. This allows the model to focus on each individual step and build a clear chain of thought. Another challenge arises when the model struggles with the reasoning steps outlined in the prompt. This can be due to ambiguity in the prompt or the model's limited understanding of the task. The solution involves providing more explicit guidance, adding intermediate prompts to clarify the reasoning steps and ensure the model stays on track. These intermediate prompts can act as checkpoints, allowing the model to demonstrate its understanding at various points during the reasoning process. Langchain experimental taught prompts get propose prompt summary. This describes the process of generating a suitable prompt for a given task using the langchain. Experimental taught prompts get propose prompt function. Inputs. This refers to the task that needs to be accomplished, clearly outlining the goal and the expected output. For example, summarize the main points of this article or write a poem about the beauty of nature. This refers to the data that will be used to generate the prompt. The data should be relevant to the task and should be in a format that can be easily understood by the language model. For example, a news article or a set of scientific papers. Outputs. This is the prompt that is generated by the function. It should be clear, concise and effective in guiding the language model to complete the desired task. For example, please summarize the main points of the following article text. Steps. This step involves analyzing the task description to understand the specific requirements and desired outcome. This includes identifying the type of task, the expected output format, and the desired level of detail. This step involves identifying the type and format of data required for the task. For example, if the task is to write a poem, the input data might be a set of keywords or a specific theme. This involves crafting the structure of the prompt in a way that effectively guides the language model to complete the task. For example, it can include specific instructions, constraints, or examples. This step involves populating the prompt structure with the relevant input data. This ensures that the language model has all the necessary information to complete the task. This involves refining and optimizing the generated prompt to improve its clarity, effectiveness, and efficiency. This can involve making changes to the wording, structure, or format of the prompt. Prerequisites. This refers to having a well-defined task, including a clear goal and the desired output. For example, write a short story about a cat is a well-defined task with a clear goal, writing a short story, and a desired output, a short story about a cat. Well-defined task, goal, and desired output are essential for creating an effective prompt. This ensures that the language model understands what it is supposed to do and what the expected output should be. This refers to having the relevant data that is needed for the task. For example, if the task is to summarize a news article, the input data would be the text of the news article. Relevant data is crucial for generating effective prompts. The data should be in a format that can be easily understood by the language model and should be relevant to the task at hand. Fine-tune parameters. This refers to the length of the prompt. A longer prompt might be necessary for complex tasks, while a shorter prompt might be sufficient for simpler tasks. This refers to the level of detail included in the prompt. A more specific prompt might provide detailed instructions and constraints, while a less specific prompt might leave more room for the language model to interpret the task. This refers to the overall structure of the prompt. A well-structured prompt is clear, concise, and easy to understand. This can include using bullet points, numbered lists, or other formatting techniques. Challenges and fixes. This refers to a task description that is unclear or ambiguous. This can make it difficult for the language model to understand what it is supposed to do. Clarifying the task goal by providing more specific instructions or examples can help address this challenge. For example, instead of saying write a story, it might be more helpful to say write a short story about a cat who is afraid of the dark. This refers to not having enough relevant data to generate an effective prompt. This can make it difficult for the language model to complete the task successfully. Providing necessary data can help address this challenge. For example, if the task is to write a poem about a specific topic, the input data might include a set of keywords or a list of related concepts. This refers to a prompt that is too complex or difficult for the language model to understand. This can lead to the language model generating inaccurate or nonsensical output. Simplifying the prompt structure by breaking it down into smaller, more manageable steps can help address this challenge. For example, instead of asking the language model to write a poem about the beauty of nature, it might be more helpful to ask it to write a line about the beauty of nature. Then write another line about the beauty of nature. And so on. This refers to a prompt that is not effective in guiding the language model to generate the desired output. This can happen if the prompt is too vague, too specific, or poorly structured. Iterative refinement is a process of continually improving the prompt by making small changes and testing the results. This can involve adjusting the wording, structure, or format of the prompt, as well as adding or removing specific instructions or constraints. langchainexperimental.toTprompts.getCaught This component is designed to generate prompts that guide a language model to solve a problem by thinking through the solution step by step. It provides a structured approach to problem solving, encouraging the model to break down tasks into smaller, manageable steps. Inputs. The input is the task or problem that the language model needs to solve. This could be a simple instruction, a question, or a more complex task. For example, the input could be write a short story about a robot who discovers a hidden world. What is the capital of France? Or design a website for a local bakery. This input is an optional list of tools that can be used to solve the problem. These tools could be application programming interfaces (APIs), online services, or any other resources that can assist the model in finding the solution. An example of this input could be a list of weather APIs that the model can use to provide information about current weather conditions. Outputs. The output of this component is a prompt that guides the language model to solve the problem by reasoning step by step. This prompt is designed to encourage the model to think through the problem logically and break it down into manageable steps. For example, the output might be a prompt that asks the model to first identify the key elements of the story, then write an outline, and finally write the full story. Steps. This step involves identifying the necessary steps to solve the problem. This might involve breaking down the problem into smaller steps, identifying the required knowledge or skills, or listing the tools needed. For example, if the problem is to write a short story, this step might involve identifying the story's setting, characters, plot, and theme. This step focuses on crafting a prompt that guides the language model through the identified steps. This could involve providing instructions, questions, or examples to help the model reason and solve the problem. For example, the prompt could ask the model to first describe the setting of the story. What is the location, time period, and atmosphere? Next, introduce the main character. What is their name, age, and motivation? Prerequisites. A clear understanding of the problem and the steps involved in solving it is essential for generating a good prompt. This understanding allows the component to break down the problem into meaningful steps and create a prompt that effectively guides the model towards a solution. understanding of the problem and steps to solve it. For instance, if the task is to write a short story, the component needs to understand the elements of a story such as plot, character, setting, and theme. Knowledge of the available tools and how they can be used to solve the problem is crucial. This knowledge allows the component to incorporate relevant tools into the prompt, empowering the model to leverage external resources. An example would be if the problem is to provide weather information for a specific location. The component needs to know about weather apps and how to use them to retrieve the necessary data. Fine-tune parameters. This parameter allows you to control the level of detail required in the steps outlined in the prompt. More detailed steps can help the language model reason more effectively. For example, if the task is to write a short story, the prompt can be fine-tuned to include more detailed steps, such as providing specific prompts for describing the characters' motivations or outlining the plots. Rising action. This parameter controls the complexity of the language used in the prompt. Simpler language might be easier for the language model to understand. For instance, if the task is complex, the prompt can be fine-tuned to use simpler language and shorter sentences to make it easier for the language model to comprehend. Challenges and fixes. The generated prompt might be too complex or too simple for the language model to understand. This can lead to the model struggling to follow the steps or misunderstanding the problem. To fix this, the component can be fine-tuned to adjust the complexity of the prompt based on the language model's capabilities. If the model is struggling with a complex prompt, it can be simplified. Conversely, if the model seems to be understanding the problem easily, the prompt can be made more challenging. The language model might not be able to effectively reason through the steps or use the tools correctly. This could be due to limitations in the model's reasoning abilities or lack of training on specific tools. To address this challenge, the component can be improved by incorporating techniques that enhance the model's reasoning abilities. This could involve using techniques like chain of thought prompting or providing more explicit instructions on how to use tools. Additionally, the component can be trained on a dataset that includes examples of using the relevant tools to solve problems. langchainexperimental. Prompts.getCaught This function is designed to generate prompts for chain of thought caught reasoning. Chain of thought reasoning is a technique used to improve the performance of language models on tasks that require logical reasoning by encouraging the model to break down a complex problem into a series of smaller steps. Inputs. The input to this function is a question or task that needs to be solved using chain of thought reasoning. For example, the question could be what is the capital of France? Or the task could be write a short story about a cat. Outputs. The output of this function is a prompt specifically designed for chain of thought reasoning. The prompt will guide the model through a series of reasoning steps in order to arrive at a solution. Steps. The function first constructs a prompt based on the input question or task. This initial prompt may be a simple statement of the task, such as answer the following question: what is the capital of France? Next, the function incorporates chain of thought reasoning by providing a template that encourages the model to break down the problem into a series of steps. This template might include phrases like let's think step by step or first we need to, followed by a list of potential reasoning steps. Prerequisites. Understanding of chain of thought. Chain of thought is a technique in which a language model is encouraged to explicitly state its reasoning process in order to solve a problem. This is achieved by prompting the model to generate a series of intermediate steps. or thoughts, leading to the final answer. For example, if a model is asked to solve a simple arithmetic problem, it might be prompted to write out each step of the calculation, making its reasoning process more transparent and understandable. Knowledge of prompt engineering. Prompt engineering refers to the art and science of designing effective prompts for language models. This involves understanding the capabilities of the model, as well as the specific task at hand. By carefully crafting prompts, we can guide the model towards generating desired outputs. Fine-tune parameters. Template for CORT reasoning. The template is a key component of a CORT prompt. It provides the model with a structure for its reasoning process, suggesting how it should break down the problem into smaller steps. This template can be tailored to the specific task at hand. For example, for a question answering task, the template could include phrases like first, let's identify the key information in the question, followed by next, we need to search for relevant information in the provided text, and finally, based on the information we found, we can conclude that number of reasoning steps. The number of reasoning steps specified in the prompt can influence the complexity of the model's reasoning process. A larger number of steps allows for more detailed and nuanced reasoning, while a smaller number of steps might be suitable for simpler tasks. It's important to strike a balance between providing enough guidance for the model to reason effectively without overwhelming it with too many steps. Challenges and fixes. Incorrectly formatted prompt. A poorly formatted prompt can confuse the model and lead to incorrect or irrelevant responses. This might happen if the prompt is ambiguous, incomplete, or uses language that the model doesn't understand. To fix this, ensure the prompt is well structured and understandable for the model. The prompt should be clear, concise, and free from grammatical errors. It should also be relevant to the task at hand. Model fails to follow CORT reasoning sometimes. Even with a well-formatted prompt, the model might not follow the reasoning steps outlined in the prompt. This can happen if the model lacks the necessary knowledge or understanding of the task, or if the prompt doesn't provide enough guidance. To fix this, adjust the prompt template or provide more specific instructions. For example, you could try adding more specific guidance within the reasoning steps, or providing the model with examples of how to solve similar problems using CORT reasoning. langchainexperimental. Prompts.get propose prompt summary. This tool is designed to create effective prompts for various tasks, aiming to guide language models to generate desired outputs. Inputs. The task description outlines the goal or the desired outcome the prompt should guide the model to achieve. For instance, summarize the key findings of the article on climate change. Task constraints refer to specific limitations or specifications that the prompt must consider. Examples include word limit, style, or the type of information required. Such constraints help refine the model's output and make it suitable for the intended purpose. Outputs. The tool generates a prompt that is well suited to the task. This prompt is a structured input given to the language model to elicit a specific response. The prompt may incorporate specific instructions, examples, or formatting guidelines depending on the task requirements. Steps. Identifying the task objective involves pinpointing the precise goal or desired outcome the prompt should guide the language model to achieve. For example, if the task is to summarize a news article, the objective could be to identify the key events, the main actors involved, and the central theme of the article. Identifying constraints involves recognizing any limitations or specifications that the prompt must consider. Examples include a word limit for the summary, the need for a neutral tone, or the requirement to include specific types of information. Developing prompt structure refers to creating the framework or format for the prompt. This involves deciding on the way information will be presented to the model, including the use of instructions, examples, and formatting techniques. For instance, a prompt might include a set of questions to guide the model, provide a specific context for the task, or set a tone for the response. Populating the prompt with details involves filling in the prompt structure with specific information relevant to the task. This step involves adding the actual text of the task description, the constraints, and any additional context or examples that could help the model understand the task. Prerequisites. Task understanding involves thoroughly comprehending the desired outcome and the context of the task. This involves understanding the specific requirements of the task, the expected output, and the potential challenges involved. For example, before generating a prompt for summarizing a scientific paper, one must understand the paper's key arguments, the intended audience, and the expected level of detail in the summary. Examples for understanding the task could include having a clear understanding of the input data, the desired format for the output, the intended audience, and the potential implications of the task. It could also involve being aware of any biases or limitations of the data or the task itself. Prompt engineering skills involve designing effective prompts that elicit desired responses from language models. This involves understanding the capabilities and limitations of the model, using appropriate language and structure, and incorporating relevant examples and instructions. For instance, a good prompt for summarizing a news article could incorporate a specific format for the summary, a word limit, and instructions to avoid personal opinions. Examples of prompt engineering skills could include incorporating different prompt styles like few-shot learning, zero-shot learning, or chain-of-thought prompting, depending on the task and the model's capabilities. It could also involve utilizing techniques like question answering, text generation, and code generation prompts, tailored to the specific task requirements. Fine-tune parameters. Prompt format refers to the overall structure and organization of the prompt. This includes the order of instructions, the use of examples, and the formatting of the prompt itself. For instance, a prompt might be structured as a set of questions, a list of instructions, or a combination of both. Prompt length refers to the number of words or characters in the prompt. A shorter prompt might be more concise and straightforward, while a longer prompt can provide more detailed instructions and examples. The ideal length depends on the complexity of the task and the specific requirements of the prompt. Prompt clarity involves using clear and unambiguous language to avoid confusion or misinterpretations. A well-written prompt should be easily understood by the language model and should guide the model to generate the desired output. This often involves using specific and concrete language, avoiding jargon, and providing clear examples, challenges and fixes. An overly general prompt can lead to ambiguous or irrelevant responses from the language model. This happens when the prompt lacks specific instructions or examples, leaving the model to interpret the task in its own way. Fixing this involves specifying the task details with clarity and precision. This could include providing a specific context for the task, outlining the expected format for the output, and providing specific examples of what is considered a successful response. An ambiguous prompt can lead to the model generating responses that are not aligned with the intended purpose. This can occur when the prompt uses unclear language or provides conflicting instructions, leaving the model uncertain about the desired outcome. Fixing this involves clarifying the instructions, using precise language, and removing any ambiguity or conflicting information from the prompt. This could include rephrasing the instructions, providing additional context, or offering concrete examples of desired responses. A too lengthy prompt can overwhelm the language model and make it difficult to process all the information. This can lead to the model generating responses that are not fully relevant to the task or that are poorly structured. Fixing this involves adopting a concise prompt structure by removing unnecessary information and focusing on the essential instructions and examples. This could involve prioritizing the most important details, removing redundancy, and using a clear and concise language. Langchain experimental utilities. A collection of experimental tools and features designed to expand LangChain's capabilities. These utilities are designed to push the boundaries of what is possible with LangChain, providing innovative ways to interact with and process data. Inputs, text, code, data, or other inputs depending on the specific utility. This could be anything from a simple text prompt to a complex dataset or code snippet. The specific input required will vary depending on the function of the utility. For example, a text summarization utility might take a long article as input, while a code completion utility might take a partially written program. Configuration settings for the utility. These settings allow you to control the behavior of the utility, such as the model used, the temperature of the response, or the maximum length of the output. By tweaking these settings, you can fine-tune the utility to your specific needs. For instance, you could adjust the temperature of a text generation utility to control the creativity of the generated text, or set the maximum length of a summarization utility to control the desired length of the summary. Outputs. Processed outputs like text summaries, code completions, or generated content. The output of the utility will depend on its function. Some examples include text summarization, a short summary of a longer text document. Code completion, suggestions for completing a partially written program. Text generation, creative text outputs based on a given prompt. Data analysis, insights and interpretations from a given dataset. Insights and analysis based on the processed input. Beyond simply generating outputs, these utilities can also provide insights and analysis on the input data. For example, a sentiment analysis utility could provide insights into the emotional tone of a text, while a data analysis utility could identify trends or patterns in a dataset. Steps. Load and configure the chosen utility. This involves selecting the specific utility you need and configuring its settings based on your requirements. The configuration might involve specifying the model to use, setting parameters like temperature or top P, and defining any necessary constraints for the utility. Provide input data to the utility. Once the utility is configured, you need to provide the input data that the utility will work with. This could involve loading a text file, entering a prompt, or importing a dataset. The specific input format will be determined by the utility you are using. Execute the utility's functions. Once the input data is provided, you can execute the utility's functions. This involves running the selected utility with the chosen configuration and input data. During execution, the utility will process the data according to its defined functions and generate the desired outputs. Process and output the results. The utility's execution will produce results that need to be processed and outputted in a meaningful format. This might involve formatting the output as text, generating a file, or displaying the results in a user interface. The output format will depend on the specific function of the utility and the desired outcome. Prerequisites: LangChain installed. To use these experimental utilities, you need to have LangChain installed in your environment. You can install LangChain using pip install langchain. Basic understanding of LangChain concepts. Familiarity with basic LangChain concepts like chains, tools, and agents is helpful for using these experimental utilities effectively. Understanding these concepts will help you grasp how the utilities are designed and how they interact with other parts of the LangChain framework. Fine-tune parameters. Model parameters for specific utilities like temperature and top P. These parameters control the behavior of the underlying language models used by the utilities. For example, temperature influences the randomness and creativity of the generated text, while top P controls the probability distribution of the output tokens. Adjusting these parameters allows you to fine-tune the utility's output according to your specific needs. Configuration settings for the utility's behavior. In addition to model parameters, there are other configuration settings that affect the utility's behavior. These settings could include things like the maximum length of the output, the number of results to generate, or the specific constraints to apply to the output. By adjusting these settings, you can tailor the utility's behavior to your specific use case. Challenges and fixes. Error handling for unexpected inputs or scenarios. Real-world data can be unpredictable, and utilities may encounter unexpected input types or scenarios. Implementing robust error handling mechanisms and logging is crucial to address these issues. For example, if a utility expects a specific input format, it should be able to handle cases where the input does not conform to that format. Performance optimization for complex tasks. Complex tasks involving multiple utilities or large datasets can be computationally demanding. Optimizing performance is crucial for efficient execution. Techniques like caching, parallelization, and efficient resource utilization can enhance performance, ensuring that the utilities can handle complex tasks effectively and efficiently. Security considerations for sensitive data. When dealing with sensitive data, security is a paramount concern. Implementing appropriate security measures like data sanitization, access control, and encryption is essential to protect data from unauthorized access or modification. These measures ensure that the utilities handle sensitive data responsibly and securely. Integration with external systems to leverage the full potential of LangChain. These experimental utilities should be able to integrate seamlessly with other external systems and services. Developing clear interfaces and documentation for integration ensures compatibility and smooth data exchange, enabling the utilities to work in conjunction with other tools and platforms. LangChain experimental tote prompts get propose prompt. This section provides a detailed explanation of the LangChain experimental tote prompts get propose prompt function, including its purpose, inputs, outputs, steps involved, prerequisites, fine-tuning parameters, and common challenges and their resolutions. Inputs. This refers to the task description that is provided as input to the LangChain experimental tote. Prompts get propose prompt function. The task description should be clear and specific, outlining the desired outcome. For example, a task description could be write a blog post summarizing the latest advancements in artificial intelligence. Outputs. The output of the LangChain experimental tote prompts get propose prompt function is a prompt to propose a new prompt. This prompt is designed to be used as input to another language model (LM) or prompt engineering tool. The proposed prompt should be tailored to generate the desired output for the specified task. For instance, a proposed prompt could be write a blog post that summarizes the key breakthroughs in artificial intelligence in the past year, focusing on the advancements in specific area of AI. Steps. This step involves analyzing the input task description to understand its scope, desired output, and any constraints. This analysis helps in identifying the key elements that need to be included in the proposed prompt. For example, analyzing the task, write a blog post summarizing the latest advancements in artificial intelligence, would involve identifying the desired length of the blog post, the target audience, and the specific areas of AI to be covered. This step focuses on formulating a prompt that, when used as input to a language model, will generate a new prompt specifically designed for the given task. The formulated prompt should guide the LM to produce a prompt that is relevant, specific, and effective in generating the desired output. Prerequisites. A well-defined task is crucial for generating a relevant and effective prompt. Ambiguity in the task description can lead to unclear prompts and ultimately inaccurate outputs. It is important to clearly define the desired outcome, the scope of the task, and any specific requirements. Experience in prompt engineering is essential for effectively using the langchain experimental tote. Prompts get propose prompt function. Prompt engineering involves crafting prompts that elicit specific and desirable responses from language models. Familiarity with prompt engineering techniques, such as prompt chaining, few-shot learning, and prompt engineering frameworks, is beneficial for creating effective prompts. Fine-tune parameters. This refers to the specific techniques and strategies used in prompt engineering to optimize the generated prompts. These techniques can include using different prompt structures, incorporating context, providing examples, and fine-tuning the prompt based on initial results. Challenges and fixes. An ambiguous task can lead to unclear prompts and inaccurate outputs. To resolve this, it is necessary to clarify the task by providing a more precise description of the desired outcome, scope, and specific requirements. For example, instead of write a summary of the latest AI advancements, the task could be clarified as write a concise summary of the key breakthroughs in natural language processing in the past year, focusing on advancements in machine translation. A task that is too broad can result in overly general prompts and outputs that are not tailored to the specific needs. To address this, it is necessary to break down the task into smaller subtasks. For instance, the task write a report on the impact of AI on the healthcare industry could be broken down into subtasks such as research the current use cases of AI in healthcare, analyze the ethical implications of AI in healthcare, and explore the potential future applications of AI in healthcare. A task that is too narrow can limit the potential of the prompt and output. To overcome this challenge, it is important to expand the task scope by providing a broader context and including more relevant details. For example, the task generate a list of movies starring Tom Hanks could be expanded to generate a list of movies starring Tom Hanks, including the year of release, genre, and critical reception. Langchain experimental utilities Python REPL summary. A utility for running Python code in a read evaluate print loop environment using LangChain. LangChain is a framework for building applications that use large language models. Inputs. Python code to execute. The Python code can be any valid Python code that can be executed in a REPL environment. For example, you can provide code to define functions, create variables, or perform calculations. optional context or data to use in the code. This input can be used to provide additional information or data that the Python code can access and use. For example, you could provide a dictionary of data or a list of strings. Outputs. The output of the executed Python code. This output will be the result of executing the Python code in the REPL environment. For example, if you execute a function that returns a value, the output will be that value. Steps. Initialize a Python REPL instance. A Python REPL instance is an object that provides a REPL environment for executing Python code. Pass the Python code to the REPL instance. This step involves providing the Python code to the Python REPL instance so that it can be executed. Execute the code and capture the output. The Python REPL instance executes the Python code and captures the output. Prerequisites. LangChain library installed. LangChain is a framework for building applications that use large language models. Python 3.7 or later. Python is a high-level, general-purpose programming language. It is used for a wide range of applications, including web development, data science, machine learning, and more. Fine-tune parameters. Global's dictionary of global variables to use in the REPL environment. Global variables are variables that are accessible from anywhere in a program. Local's dictionary of local variables to use in the REPL environment. Local variables are variables that are only accessible within a specific scope, such as a function. Challenges and fixes. Code execution errors. Code execution errors can occur for a variety of reasons, such as syntax errors, runtime errors, or logical errors. Debug the code for errors. Potentially using a debugger. A debugger is a tool that allows you to step through code line by line, inspect variables, and identify the cause of errors. Access to external resources. The Python code may need to access external resources, such as files, databases, or network services. Define and import necessary libraries within the code. Libraries are collections of code that provide functionality for specific tasks. For example, the requests library can be used to make HTTP requests. LangChain experimental video captioning. This module is a robust tool for generating captions for videos, leveraging the capabilities of LangChain, a powerful framework for building applications with large language models. Inputs. This module takes as input the path to the video file that you want to caption. This could be a local file path or a URL pointing to the video. You need to specify the name of the language model you want to use for caption generation. Examples include GPT 3.5 Turbo, which is a powerful text generation model from OpenAI. Outputs. The output of this module is a list of captions corresponding to different segments of your video. Each caption summarizes the content of its associated segment. Steps. The first step is to load the video file into the module. This ensures that the module can access the video data. The module then extracts individual frames from the video. Each frame represents a still image at a particular point in time within the video. The module employs a vision model, such as clip, to generate embeddings for each extracted frame. An embedding is a numerical representation of the frame's visual content. These embeddings are then used to cluster the frames based on their visual similarity. Frames with similar embeddings are grouped together, forming clusters that represent distinct segments within the video. Using a language model, the module generates captions for each cluster. The model analyzes the visual information encoded within the cluster's frames and creates a concise, textual description that captures the essence of the cluster's content. The individual captions for each cluster are combined to form a complete caption for the entire video. This provides a comprehensive summary of the video's content, aligned with its visual segments. Prerequisites. Before using the video captioning module, you need to install certain essential libraries. LangChain. This Python library provides a framework for building applications using large language models. It simplifies the process of integrating language models into your applications. OpenAI. This library allows you to access and use the powerful language models offered by OpenAI, such as GPT 3.5 Turbo. OpenCV Python. This library provides tools for processing and analyzing images and videos. It is used in this module for tasks like frame extraction and image manipulation. To run the video captioning module, you need to have access to a vision model and a language model. Vision models, like Clip, are used to analyze the visual content of the frames, while language models, such as GPT 3.5 Turbo, are used for text generation. Specifically the captions. Fine-tune parameters. This parameter allows you to control the number of clusters that the frames will be grouped into. By adjusting this parameter, you can influence the granularity of the video segmentation, determining the number of distinct segments the captions will describe. The caption length parameter defines the desired length of the generated captions. You can fine-tune this parameter to control the level of detail and conciseness in the generated captions. Challenges and fixes. One challenge in video captioning is handling poor video quality, which can affect the accuracy of frame analysis and caption generation. Using image denoising techniques can help improve the quality of the video frames, leading to more accurate analysis and better captions. Another challenge is inaccurate frame clustering, which can result in segments that do not accurately reflect the visual content of the video. Experimenting with different clustering algorithms, such as k-means clustering or hierarchical clustering, can improve the accuracy of frame grouping, leading to more meaningful video segments and captions. Sometimes, the generated captions may not accurately align with the video content, potentially misinterpreting the visual information or lacking relevant context. Fine-tuning the language model with relevant video data can help improve its understanding of visual cues and context, leading to more accurate and relevant captions. This can involve providing the model with examples of video caption pairs, allowing it to learn the relationship between visual content and corresponding text descriptions. Prerequisites. OpenAI Application Programming Interface Key. An OpenAI Application Programming Interface API key is required for the model to access OpenAI's powerful language models. This key acts as an authorization token, allowing the model to use OpenAI's services, such as generating text or understanding language. It is typically obtained by creating an account on the OpenAI platform. Hugging Face Token. A Hugging Face token is necessary for interacting with the Hugging Face Model Hub. This token provides access to a wide range of pre-trained models, which are essential for tasks like natural language understanding and generation. It is often obtained by registering an account on the Hugging Face platform. Fine-tune parameters. Model name. This parameter allows for fine-tuning the model to specific needs. It allows users to select the most appropriate pre-trained model from Hugging Face's repository for their specific video captioning task. By adjusting the model name, users can choose models with different strengths and weaknesses, tailoring the model to their specific video content. Temperature. The temperature parameter controls the creativity and diversity of the model's output. It allows users to adjust the level of randomness in the generated captions. ranging from more predictable and consistent output to more creative and diverse captions. A higher temperature value introduces more randomness and potentially leads to more unusual and imaginative captions, while a lower value results in more predictable and consistent outputs. Challenges and fixes. Video file size too large. Large video files can be challenging for the model due to computational constraints. To address this, users can consider using a smaller video file, which would reduce the processing burden. Alternatively, utilizing a video compression tool to reduce the size of the video while maintaining its content integrity can also be effective. Video format not supported. The model might not support all video formats. If the video is in an unsupported format, converting it to a supported format, such as MP4, is necessary. This ensures compatibility with the model's processing capabilities and allows for successful caption generation. Langchain experimental video captioning. This YAML document elaborates on each scalar value within the context of the YAML, providing more detailed descriptions and real-world examples. Inputs: a URL pointing to a video file hosted online. This could be a link to a video on YouTube, Vimeo, or any other video hosting platform. For instance, a YouTube video URL could be https://www.youtube.com/watch VDQW4W9WGXCQ. The file path to a video file stored locally on the system. This path can be absolute, e.g. home user videos myvideo.mp4 or relative, e.g. videosmevideo.mp4 depending on the system's file structure and the location of the video file. Outputs: the generated captions for the input video in text format. These captions will describe the content of the video, including speech and actions, making it accessible to users who are deaf or hard of hearing or those who prefer to read the content rather than watch it. Steps: the video is first uploaded to the system either through the provided URL or by accessing the local file path. This allows the system to process the video data for caption generation. The video is then processed by a pre-trained model. This model has been trained on a massive dataset of video and caption pairs, enabling it to learn the relationship between visual and textual content. This processing step might involve various techniques like frame extraction, feature extraction, and language modeling, depending on the specific model used. The pre-trained model uses the processed video data to generate the captions. The model analyzes the visual information in each frame and generates text that accurately describes the actions, objects, and speech in the video. Prerequisites: a pre-trained model that is specialized in video captioning is required. Such models are trained on large datasets and are capable of understanding video content and generating relevant captions. OpenAI Clip Contrastive Language Image Pre-training is a powerful model developed by OpenAI. It is trained on a massive dataset of image-text pairs, allowing it to learn the relationship between visual and textual content. Clip can be used for various tasks, including video captioning, by leveraging its understanding of both visual and textual information. Google Vision API is a cloud-based service provided by Google that offers various vision-related functionalities, including image and video analysis. It utilizes powerful pre-trained models to perform tasks like object detection, image classification, and text recognition. The Vision API can be used in conjunction with other language models to generate captions for videos, leveraging its image understanding capabilities. The input video should be provided in a format that is recognized and supported by the system. This can be either a URL pointing to a video file hosted online or a file path to a video file stored locally. The system should be able to handle various video formats like MP4, AVI, MOV, etc. Fine-tune parameters. The specific model used for video captioning can be selected based on the requirements of the task. This allows users to choose a model that is best suited for the specific type of videos they are working with. For instance, some models might be better suited for generating captions for educational videos, while others might be better suited for generating captions for entertainment videos. The batch size refers to the number of video clips processed simultaneously by the model. This parameter can be adjusted based on the available computational resources and the desired processing speed. A larger batch size can lead to faster processing but might require more memory, while a smaller batch size might be more efficient for systems with limited resources. Challenges and fixes. The model might not always generate completely accurate captions. This can be due to various factors, such as the complexity of the video content, the quality of the video, or limitations in the model itself. To improve accuracy, the model can be fine-tuned with additional data relevant to the specific type of videos being processed. This fine-tuning process involves training the model on a new dataset that contains examples of videos and their corresponding captions, allowing the model to learn from the new information and improve its performance. Some models might not support all video formats, leading to difficulties in processing specific types of videos. This could be due to limitations in the model's architecture or the lack of training data for certain video formats. To address this challenge, the system should be updated to support more video formats. This can involve expanding the model's capabilities to process new formats or incorporating additional models that specialize in specific formats. This ensures that the system can handle a broader range of video inputs, improving its versatility and applicability. Langchain Experimental Video Captioning Models Base Model Summary. NaN. A base class for video captioning models in LangChain. It provides a foundation for building and using video captioning models within the LangChain framework. Inputs. The path to the video file or a URL pointing to the video. The model will take this video as input and generate a textual description of the video content. These are optional parameters that can be used to configure the model. They provide flexibility in controlling the behavior of the video captioning model. For example, adjusting parameters might allow you to control the length of the caption or the level of detail in the generated description. Outputs. The output of the model is a textual description of the video content. This caption summarizes the key events and actions depicted in the video, making it easier to understand and analyze the visual information. Steps. The video file is loaded, marking the initial step in the video captioning process. This step involves retrieving the video data from the specified path or URL. The video frames are extracted, dividing the video into individual still images. This allows the model to analyze the video frame by frame, identifying key visual elements and changes in the scene. The model generates captions for each individual frame. By analyzing the visual content of each frame, the model generates a textual description that captures the key events and objects present in that specific moment in the video. The individual captions for each frame are combined into a coherent narrative. This involves arranging the captions in a logical order and connecting them to form a fluent and understandable description of the video. This step ensures that the generated caption flows naturally and accurately reflects the overall story of the video. Prerequisites. The ability to perform video captioning requires a dedicated video captioning model. This model is trained to understand the relationship between visual content and textual descriptions. OpenAI's Clip Contrastive Language Image Pre-training model is a powerful tool for image and text understanding. It can be used to generate video captions by learning to associate visual features with textual descriptions. Google's Vision Transformer model is an advanced deep learning architecture specifically designed for image recognition tasks. It can be used for video captioning by analyzing the visual content of frames and generating descriptive captions. The process of video captioning involves working with video data. This necessitates the use of a video processing library that can handle tasks like reading, analyzing, and manipulating video files. OpenCV is an open-source computer vision library that offers a comprehensive set of tools for working with video data. It provides functionalities for video capture, processing, analysis, and display. FFmpeg is a powerful multimedia framework that allows for manipulation and conversion of video and audio data. It provides functionalities for video encoding, decoding, and transcoding, which are essential for video processing in video captioning. Fine-tune parameters. Model weights represent the learned parameters of the video captioning model. Fine-tuning these weights involves adjusting them based on a specific dataset of videos and captions, allowing the model to better adapt to the characteristics of that particular dataset. The learning rate controls how much the model adjusts its weights during training. Fine-tuning the learning rate can affect the speed and accuracy of the model's training process. By adjusting the learning rate, you can optimize the model's performance for specific datasets and tasks. Challenges and fixes. A key challenge in video captioning is generating captions that accurately reflect the video content. This requires the model to understand the visual information, identify key events and actions, and express them in a clear and concise way. Using a more robust video captioning model can improve accuracy. Models with more advanced architectures and trained on larger datasets are better equipped to handle complex visual scenarios and generate more accurate captions. Fine-tuning the model on a large dataset of videos and captions can significantly enhance its performance. This process allows the model to learn the nuances of specific video styles and contexts, leading to more accurate and contextually relevant captions. Maintaining a coherent narrative flow in the captions is another challenge. The captions should not only describe individual frames but also connect them into a logical and understandable story. Using a language model to generate captions can improve coherence and fluency. Language models are trained on large amounts of text data, enabling them to generate grammatically correct and natural-sounding captions. Implementing a post-processing step to ensure that the captions are grammatically correct and flow well together can enhance readability and comprehension. This step involves checking the generated captions for grammatical errors and ensuring that they form a smooth and coherent narrative. 0.7. A value between 0 and 1 that controls the randomness of the generated output. Higher values will lead to more creative outputs, while lower values will lead to more predictable outputs. Max tokens. 1000. The maximum number of tokens that the OpenAI model should generate. A token is typically a word or part of a word. Top P. 1. The probability threshold to use for nucleus sampling. This is a technique used to generate more focused outputs. Frequency penalty. 0. A value between 0 and 1 that controls the penalty for using words that have already been used frequently. Higher values will lead to less repetitive outputs. Presence penalty 0. A value between 0 and 1 that controls the penalty for using words that have already been used. Higher values will lead to less repetitive outputs. Challenges and fixes. Video URL is invalid. Check URL and use valid URL for video. The provided video URL is not a valid URL or does not point to a video. Caption retrieval fails. Provide a caption file or implement a caption retrieval method. The video caption retrieval failed. This may be due to the video not having captions available, or the caption retrieval method failing. OpenAI API errors. Check API key and ensure OpenAI service is working correctly. The OpenAI application programming interface service is not working correctly. This could be due to a problem with your API key or a problem with the OpenAI service itself. langchainexperimental. Prompts.get propose prompt. Description of langchainexperimental. Prompts get propose prompt. Inputs. The specific task that the prompt is intended to accomplish. For example, write a poem about a cat or summarize this article about machine learning. Information about the user's personality and preferences, which could include things like their interests, writing style, or desired tone. Outputs. A well-crafted prompt that is designed to generate a high-quality output from a language model. The prompt should be clear, concise, and provide enough context for the model to understand the desired outcome. Steps. Obtain the user's persona if it is available. This can be done through a variety of methods, such as asking the user to provide their persona or using a user profiling system to infer their personality traits. Construct the prompt string by incorporating the task and user persona information into a well-structured format. This may involve using specific prompt engineering techniques to ensure the prompt is effective and elicits the desired response from the language model. Prerequisites. Having access to the user's persona information is beneficial but not always essential. If the user's persona is not available, alternative prompt engineering techniques can be employed. A clear and well-defined task is crucial for the prompt to be successful. The task should be specific and achievable, providing the language model with a clear goal to strive for. Fine-tune parameters. The prompt engineering techniques used, such as using specific keywords, providing context, or framing the task in a specific way, can significantly influence the quality of the generated output. The format of the prompt being proposed can also have a substantial impact on the model's performance. Different prompt formats, such as using specific question formats, providing examples, or incorporating constraints, can lead to varying results. Challenges and fixes. The prompt generated might not be optimal from the first attempt. It's crucial to iterate and refine the prompt until it consistently produces the desired results. This involves testing the prompt with different language models, analyzing the generated outputs, and making adjustments based on the results. The user's persona might not be available in some cases. This can occur when the user is new or has not provided their persona information. In such cases, effective prompt engineering techniques can be employed to compensate for the lack of user persona data and generate high-quality outputs based on the task description alone. For example, the prompt could be structured to elicit a more neutral or general response that is not specific to a particular user's preferences. Google Cloud Storage Bucket. You'll need a Google Cloud Storage Bucket to store the video file that you want to process. Google Cloud Storage provides a secure and reliable platform for storing your data in the cloud. You can create a bucket in the Google Cloud Console, providing a dedicated space for your video files. Fine-tune parameters. Summarization model. The summarization model is a critical component of the caption processor service. It determines how effectively the captions are summarized. Fine-tuning this model allows you to tailor the summarization process to your specific needs. For instance, you might adjust the model to generate longer or shorter summaries, focusing on specific topics or themes, or adapting the language style. Caption generation model. The caption generation model plays a crucial role in producing captions for each frame of the video. Fine-tuning this model empowers you to customize the caption generation process. You might adjust the model to generate captions in a specific language, fine-tune the accuracy of the captions, or enhance the clarity of the generated captions. Challenges and fixes. Invalid video URL or file path. If you provide an invalid URL or file path, the caption processor won't be able to access the video. Ensure that the provided URL or file path is correct and points to an accessible video file. Access denied. If your Google Cloud Platform account lacks the necessary permissions to access the Google Cloud storage bucket where the video file is stored, you may encounter access denied errors. Ensure that your account has sufficient permissions to access the bucket, allowing the caption processor to read the video file. API request errors. If the caption processor encounters errors during its communication with the application programming interface API services, you may receive API request errors. These errors can occur due to network issues or problems with the API itself. In such cases, it is recommended to retry the API request with appropriate error handling mechanisms. No captions found. If the video file you provide does not contain captions, the caption processor won't be able to extract or process any captions. Check the video file for the presence of captions, ensuring that they are correctly embedded within the video. Summarization issues. If the generated summary of the captions doesn't meet your expectations, you can fine-tune the summarization model to improve the results. This may involve adjusting the model's parameters, such as the desired length of the summary, the focus of the summary, or the language style. Caption generation errors. If you encounter errors in the captions generated for each frame, you can fine-tune the caption generation model. This fine-tuning process allows you to adjust the model's parameters to improve the accuracy, clarity, and language style of the generated captions.